Imagine standing at the edge of everything you know, peering into an abyss so vast that it swallows light itself. Picture a universe where 95% of all existence is made of substances we cannot see, cannot touch, cannot even begin to understand. We are living in a cosmos that defies every intuition we possess, where the very fabric of reality bends, twists, and tears in ways that would have driven our ancestors to madness. Every night, when you look up at the stars, you're seeing less than 5% of what's actually there. The rest? It's hidden in shadows deeper than any darkness you can imagine. Right now, at this very moment, invisible particles are streaming through your body at nearly the speed of light. Trillions of them. They pass through the Earth as if it were made of nothing but empty space. These ghost particles, called neutrinos, carry secrets about the birth and death of stars, about the fundamental asymmetry that allows you to exist at all. Think about that. There's a reason you're made of matter and not antimatter, a reason this universe didn't annihilate itself in the first fraction of a second after the Big Bang. But we don't know what that reason is. Not really. We have theories, speculations, mathematical models that dance around the truth like shadows on a cave wall. But the fundamental mystery remains unsolved. What if I told you that every time you make a decision, the universe might be splitting into infinite versions of itself? That somewhere, in some other reality, another version of you chose differently? Or what if consciousness itself isn't just an accident of evolution, but a fundamental property of the universe, woven into the quantum fabric of spacetime? These aren't just philosophical musings anymore. These are serious scientific questions being investigated by researchers at the world's most prestigious institutions. Questions that are forcing us to reconsider everything we thought we knew about existence itself. Let's start with the most humbling mystery of all, the one that makes us realize just how little we understand about the universe we inhabit. Dark matter constitutes approximately 27% of everything that exists. Think about that proportion. More than a quarter of all reality is made of something we've never directly observed. We know it's there because we can see its gravitational effects, like ripples in a pond when we can't see what caused them. Galaxies spin too fast. They should be tearing themselves apart, flinging their stars into the cosmic void, but something invisible is holding them together with gravitational glue we cannot see. In the 1930s, astronomer Fritz Zwicky was studying the Coma Cluster, a collection of over 1,000 galaxies bound together by gravity. When he calculated how fast the galaxies were moving, the numbers didn't make sense. They were moving so quickly that the visible matter in the cluster couldn't possibly provide enough gravitational pull to keep them bound together. The galaxies should have scattered like marbles on a table. But they didn't. Zwicky proposed the existence of what he called Dunkel Materie, dark matter. At the time, his colleagues dismissed the idea. Decades passed before anyone took him seriously. Then came Vera Rubin, an astronomer who faced discrimination her entire career simply for being a woman in science, who would revolutionize our understanding of the cosmos. In the 1970s, Rubin and her colleague Kent Ford were measuring the rotation curves of spiral galaxies. They expected to find that stars farther from the galactic center would orbit more slowly, just as planets farther from the sun take longer to complete their orbits. That's how gravity works, right? The farther you are from the source of gravitational attraction, the weaker its pull. But galaxy after galaxy showed something impossible. Stars at the edges of galaxies were moving just as fast as stars near the center. Sometimes even faster. The only explanation was that galaxies were surrounded by massive halos of invisible matter, matter that didn't emit, absorb, or reflect light. Today, scientists are desperately searching for dark matter particles. Deep underground, in abandoned mines and specially constructed laboratories, ultra-sensitive detectors wait in absolute darkness and cold, hoping to catch a single interaction with a dark matter particle. These experiments have names like Xenon, LUX, and Super CDMS. They're built underground to shield them from cosmic rays and other particles that might create false signals. Some of these detectors use tanks filled with liquid xenon, cooled to -100 degrees Celsius. The theory is that if a dark matter particle passes through the xenon and happens to strike a nucleus, it will create a tiny flash of light and a small electrical signal that the detectors can measure. But here's the truly unsettling part. After decades of searching, after billions of dollars spent on experiments and detector technology that pushes the boundaries of human engineering, we still haven't found a single confirmed dark matter particle. Not one. The leading candidates, particles called WIMPs, or weakly interacting massive particles, continue to elude us. Some scientists have proposed alternatives, particles called axions, which would be much lighter than WIMPs. Others have suggested that dark matter might be made of primordial black holes that formed in the first moments after the Big Bang. But the truth is, we're fumbling in the dark, quite literally. Ask yourself this: what does it mean that we live in a universe where we can only perceive and understand 5% of what exists? And if dark matter is mysterious, dark energy is absolutely terrifying. It makes up approximately 70% of the universe, and it's pushing everything apart, accelerating the expansion of space itself. Imagine discovering that 3/4 of all existence is composed of an energy field that works opposite to gravity, that instead of pulling things together, it's driving them apart faster and faster, with no end in sight. This is the reality we inhabit. The discovery of dark energy came about through one of the most important astronomical observations of the late 20th century. In 1998, two teams of astronomers were studying Type Ia supernovae, stellar explosions that are so consistent in their brightness that they can be used as cosmic measuring sticks. These researchers wanted to measure how fast the universe was expanding, and they expected to find that the expansion was slowing down. After all, gravity should be acting as a brake, gradually pulling everything back together, right? But the data showed something nobody expected. The expansion of the universe wasn't slowing down. It was speeding up. Distant supernovae were farther away than they should have been if the universe was expanding at a constant or decreasing rate. This could only mean one thing. Some kind of energy was pushing space apart, counteracting gravity on cosmic scales. The scientists called this mysterious force dark energy, and in 2011, Saul Perlmutter, Brian Schmidt, and Adam Rees won the Nobel Prize in Physics for this discovery. But winning a Nobel Prize doesn't mean we understand what dark energy actually is. We don't. Some physicists think it might be related to the cosmological constant, a term that Einstein introduced into his equations of general relativity and later called his biggest blunder. Einstein added the cosmological constant to keep the universe static, because at the time, everyone believed the universe was eternal and unchanging. When Edwin Hubble discovered that the universe was expanding, Einstein abandoned the cosmological constant. But now it seems he might have been right all along, just for the wrong reasons. The cosmological constant represents the energy of empty space itself. According to quantum field theory, even a perfect vacuum isn't truly empty. It's seething with virtual particles that pop into existence and annihilate in fractions of a second. These quantum fluctuations should contribute to the energy density of space. When physicists calculate what this vacuum energy should be, they get a number that's wrong by a factor of 10 to the power of 120. That's not just wrong. That's spectacularly, absurdly wrong. It's the worst prediction in the history of physics. Yet something is causing the accelerated expansion, and we call it dark energy even though we have no idea what it really is. What does this mean for the future? If dark energy continues to dominate the universe's expansion, and current observations suggest it will, then the cosmos faces a cold, lonely fate called the Big Freeze. Galaxies will drift apart, accelerating away from each other until they're so far separated that they'll never be able to communicate again. Stars will exhaust their fuel and wink out one by one. The universe will grow dark and cold, approaching absolute zero. Any civilizations that survive will huddle around the dying embers of the last red dwarf stars, watching helplessly as the universe becomes an infinite expanse of frozen emptiness. This is the future that awaits us, written in the mathematics of dark energy. But let's pull back from cosmic scales and dive into something equally mysterious but infinitely more dense: black holes. These are regions of space-time where gravity has become so intense that nothing, not even light, can escape once it crosses a boundary called the event horizon. Think about that. Light, which travels at 300,000 kilometers per second, gets trapped. Black holes are places where our understanding of physics breaks down completely. At their centers lies something called a singularity, a point where matter is crushed to infinite density and the curvature of spacetime becomes infinite. Our equations produce infinities, which in physics is usually a sign that something is deeply wrong with our theories. Einstein's general relativity predicts black holes, but Einstein himself didn't believe they could actually exist in nature. He thought they were just mathematical curiosities. When Karl Schwarzschild first solved Einstein's equations to describe what we now call a black hole, he did it while serving in the German army during World War I. Schwarzschild was stationed on the Eastern Front, and he worked on the equations in the trenches between artillery barrages. He sent his solution to Einstein, who was both impressed and disturbed. Schwarzschild died shortly after from a disease he contracted in the trenches, never knowing that his solution would become one of the most important discoveries in astrophysics. For decades, black holes remained theoretical. Then, in the 1960s and 70s, astronomers started finding evidence for their existence. They discovered X-ray sources in binary star systems where an invisible massive object was pulling matter from a visible companion star. As the matter spiraled toward the black hole, it would heat up to millions of degrees and emit X-rays. The famous example is Cygnus X1, where a blue supergiant star is being devoured by an invisible companion. The black hole in that system is about 15 times the mass of our Sun, but it's compressed into a region smaller than a city. Then there are supermassive black holes, monsters lurking at the centers of galaxies with masses millions or billions of times greater than the Sun. Our own Milky Way harbors one called Sagittarius A star, weighing in at about 4 million solar masses. For years, astronomers watched stars orbiting an invisible point at the galactic center, their orbits providing undeniable proof that something massive and compact was there. One of these stars, designated S2, completes an orbit around Sagittarius A star in just 16 years, reaching speeds of 5,000 kilometers per second at its closest approach. The only thing that could cause such extreme motion is a supermassive black hole. In 2019, the Event Horizon Telescope collaboration achieved something that should have been impossible. They captured the first image of a black hole's shadow. This wasn't just a technical achievement. It was a vindication of Einstein's theory on the grandest possible scale. The black hole they imaged sits at the center of a galaxy called Messier 87, 55 million light-years away. It has a mass of 6.5 billion suns, and the image showed exactly what general relativity predicted: a dark shadow surrounded by a bright ring of superheated matter. When that image was released, people around the world saw with their own eyes the distortion of spacetime itself, light being bent and trapped by gravity so intense that it creates a hole in the universe. But here's where things get truly strange. Recent research published in Physical Review Letters suggests that black holes might not be the eternal prisons we thought they were. Scientists at the University of Sheffield have proposed that black holes could transition into white holes, theoretical regions of spacetime that function as the opposite of black holes. Instead of trapping everything that falls in, white holes would expel matter and energy. According to quantum mechanics, the singularity at the center of a black hole might be replaced by a region of intense quantum fluctuations where space and time don't end but transform into something new. If this theory is correct, black holes aren't endings at all, but beginnings. They might be doorways to new universes or new regions of spacetime. Ask yourself, what happens to information that falls into a black hole? Does it disappear forever? Or is it somehow preserved and eventually returned to the universe? This brings us to the black hole information paradox, a problem that has tormented physicists for decades. Stephen Hawking showed that black holes aren't completely black. They emit radiation, now called Hawking radiation, through a quantum mechanical process that occurs near the event horizon. Over enormous timescales, this radiation causes black holes to evaporate. Eventually, even the most massive black holes will disappear completely. But here's the problem. Hawking radiation is thermal, meaning it doesn't carry any information about what fell into the black hole. If a black hole evaporates completely, taking all that information with it, we have a violation of quantum mechanics, which says that information can never be truly destroyed. This is a fundamental conflict between quantum mechanics and general relativity, and we don't know how to resolve it. Some physicists think the information is somehow encoded in the Hawking radiation in a way we don't yet understand. Others believe that black holes leave behind remnants that preserve the information. Still others think we need a completely new theory of quantum gravity to solve this paradox. Speaking of quantum mechanics, let's dive into the quantum realm, where reality becomes so bizarre that it seems designed to break human intuition. At the quantum scale, particles can exist in multiple states simultaneously, a property called superposition. An electron can be in two places at once. A photon can be both a particle and a wave. Nothing is definite until you measure it, and the act of measurement itself changes reality. This isn't philosophy, it's experimental fact, confirmed thousands of times in laboratories around the world. The famous double-slit experiment demonstrates this weirdness perfectly. Fire electrons one at a time through two slits in a barrier and let them hit a screen on the other side. Common sense says each electron should go through one slit or the other and create two bands on the screen. But that's not what happens. Instead, you get an interference pattern, alternating bands of light and dark, as if each individual electron is somehow going through both slits simultaneously and interfering with itself. The electron exists in a superposition of states, taking all possible paths, until you measure which slit it went through. The moment you measure it, the interference pattern disappears, and the electron behaves like a classical particle. It's as if the universe doesn't become real until someone looks at it. This leads to the measurement problem, one of the deepest puzzles in quantum mechanics. When does a quantum system stop being in superposition and collapse into a definite state? Is consciousness required for collapse to occur? Some interpretations say yes, that consciousness plays a fundamental role in bringing reality into existence. Others, like the many worlds interpretation, say that the universe never collapses at all. Instead, every time a quantum measurement occurs, the universe splits into multiple versions, each corresponding to a different possible outcome. In one universe, you measured the electron going through the left slit. In another, you measured it going through the right slit. Both universes are equally real, and they continue to exist in parallel, branching off into infinity. The many worlds interpretation sounds like science fiction, but it's taken seriously by many physicists because it solves some deep problems in quantum mechanics. Recently, Google's quantum computer called Willow has reignited this debate. Willow solved a computational problem in under 5 minutes that would take the world's fastest classical supercomputers longer than the age of the universe to solve. Hartmut Neven, who leads Google's quantum AI team, suggested that this achievement lends credence to the many worlds interpretation. He argues that quantum computers might be harnessing computational power from parallel universes, performing calculations across multiple branches of reality simultaneously. Critics point out that this doesn't prove the many worlds interpretation, but it's a tantalizing possibility that we might be able to test these ideas experimentally. The quantum world gets even stranger when we consider entanglement, what Einstein called spooky action at a distance. When two particles become entangled, measuring the state of one particle instantly affects the state of the other, no matter how far apart they are. You could separate entangled particles by billions of light years, and they would still be connected in this mysterious way. Einstein hated this idea because it seemed to violate the principle that nothing can travel faster than light. He thought entanglement proved that quantum mechanics was incomplete, that there must be hidden variables we hadn't discovered yet. But Einstein was wrong. Experiments have repeatedly confirmed that entanglement is real, and there are no hidden variables. In 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for experiments that definitively ruled out local hidden variable theories. The universe really is this strange. Entanglement isn't just a curiosity. It's being used to develop quantum computers and quantum communication systems. The Chinese satellite Mischius has already demonstrated quantum entanglement distribution over 1,200 kilometers, a crucial step toward a quantum internet that would be virtually unhackable. Now, let's talk about consciousness itself, perhaps the most profound mystery of all. What is consciousness? How does subjective experience arise from objective physical processes in the brain? Philosophers call this the hard problem of consciousness, and despite centuries of investigation, we're no closer to solving it. You can describe every neuron firing, every neurotransmitter being released, every electrical signal propagating through neural networks, and still, you haven't explained what it's like to see the color red, to feel pain, to experience love or wonder or despair. Recent research is exploring the possibility that quantum mechanics plays a role in consciousness. A paper published in December 2025 in Frontiers in Human Neuroscience suggests that conscious states might arise from the brain's capacity to resonate with the quantum vacuum, the zero-point field that permeates all space. According to this theory, specific frequencies of the quantum vacuum can resonate with glutamate, the brain's most abundant neurotransmitter. This resonance occurs in cortical microcolumns, groups of about 100 neurons bathed in glutamate. The interaction between the quantum field and these microcolumns might be what tunes the brain to a critical state where consciousness emerges. Another theory, proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff, suggests that consciousness arises from quantum processes and structures called microtubules inside neurons. Microtubules are tiny protein tubes that form part of the cellular skeleton. Penrose and Hameroff argue that quantum computations occur in these microtubules, and when these quantum states undergo something called orchestrated objective reduction, consciousness emerges. This theory has been controversial, but recent experiments with anesthesia are providing intriguing support. Studies have found that certain isotopes of xenon gas, which differ only in their nuclear spin, have dramatically different anesthetic potencies. Nuclear spin is a quantum property, and the fact that it affects consciousness suggests that quantum mechanics might indeed be involved in how we experience the world. If consciousness has quantum origins, the implications are staggering. Some theorists suggest that our consciousness-generating particles could be entangled with other particles throughout the universe, meaning we might be intimately connected to the cosmos in ways we can't yet comprehend. Think about what that means. Every thought, every sensation, every moment of awareness might be part of a universal quantum network, linking your mind to the fundamental structure of reality itself. Another approach, presented in AIP Advances in November 2025, proposes that consciousness is not an emergent property of neural processes but a foundational aspect of reality itself. This framework treats consciousness as a fundamental field, like the electromagnetic field or the gravitational field. According to this model, universal consciousness is the substrate through which space, time, and matter are realized. Individual consciousness arises through processes like symmetry breaking and quantum fluctuations, similar to how particles emerge from quantum fields. This is a form of panpsychism, the idea that consciousness is a basic feature of the universe, present at all levels of existence. If this is true, then even elementary particles might have some primitive form of experience. These theories remain highly speculative, but they're forcing scientists to reconsider fundamental assumptions about the relationship between mind and matter. Are we simply biological machines, with consciousness as a byproduct of complex neural computation? Or is consciousness something more fundamental, woven into the fabric of the universe itself? The question has profound implications not just for neuroscience and physics, but for how we understand our place in the cosmos. Let's shift to another cosmic mystery that challenges everything we know: the Fermi paradox. Physicist Enrico Fermi posed a simple question during a lunch conversation in 1950. Where is everybody? The universe is ancient, nearly 14 billion years old. Our galaxy alone contains hundreds of billions of stars, many of them with planets in the habitable zone where liquid water could exist. The building blocks of life, complex organic molecules, have been found in interstellar space, in comets, in meteorites. Life arose on Earth relatively quickly, within the first billion years after the planet formed. If life is common in the universe, and if even a tiny fraction of life-bearing worlds develop intelligent civilizations, and if even a tiny fraction of those civilizations develop the technology to explore or communicate across interstellar distances, then the galaxy should be teeming with evidence of alien intelligence. But we've seen nothing. No radio signals, no megastructures, no self-replicating probes. The silence is deafening. Various solutions to the Fermi paradox have been proposed, and they range from optimistic to terrifying. Maybe life is common, but intelligent life is extraordinarily rare. Maybe the development of technology inevitably leads to self-destruction. Maybe advanced civilizations exist but deliberately avoid contact with primitive species like us. Maybe they're here already, watching us, but we're too primitive to recognize them. Or maybe we're alone, the only conscious beings in an entire galaxy of barren worlds and dead rocks. That possibility is almost too terrible to contemplate. The cosmic loneliness of it, the burden of being the universe's only chance to understand itself. The Great Filter is another explanation that keeps astronomers up at night. The idea is that there's some stage in the development of life that is extraordinarily difficult to pass. Either the filter is behind us, meaning we've already passed through the incredibly unlikely steps that most planets never complete, or the filter is ahead of us, and we're doomed to fail like countless other civilizations before us. If we discover simple life, even microbial life, on Mars or the moons of Jupiter or Saturn, that would actually be bad news. It would suggest that life is common in the universe, which means the Great Filter must lie ahead of us. It would mean that something prevents civilizations from becoming spacefaring or long-lasting. Maybe it's nuclear war. Maybe it's climate catastrophe. Maybe it's artificial intelligence run amok. Maybe it's something we haven't even imagined yet. The silence of the cosmos raises another disturbing possibility: the dark forest hypothesis. Imagine the universe as a dark forest where every civilization is a hunter, creeping through the undergrowth, desperately trying to remain hidden. Any civilization that reveals its location might be destroyed by others who see it as a potential threat. In this scenario, the reason we haven't heard from anyone is that nobody wants to be found. Any species intelligent enough to communicate across interstellar distances is also intelligent enough to understand the danger. Broadcasting your presence to the cosmos might be the equivalent of lighting a campfire in a forest full of predators. Perhaps the wisest civilizations are those that remain silent, listening but never transmitting, waiting and watching in the darkness. Consider the scale of cosmic time. The Earth formed 4.5 billion years ago, but the universe is 13.8 billion years old. That means planets could have formed and life could have emerged billions of years before our solar system even existed. If an alien civilization had a mere 1 million year head start on us, and that's nothing on cosmic timescales, they could have colonized the entire galaxy multiple times over. The fact that we see no evidence of such colonization suggests something is wrong with our assumptions. Either intelligent life is far rarer than we think, or civilizations don't last long enough to colonize galaxies, or they choose not to for reasons we don't understand, or we're looking in the wrong way for the wrong things. Now let's consider one of the most fundamental mysteries. Why is there something rather than nothing? This question has puzzled philosophers and theologians for millennia, but it's also a legitimate scientific question. The universe didn't have to exist. The laws of physics didn't have to be what they are. The fundamental constants could have taken different values. So why this particular universe with these particular laws and constants? Why is there matter and energy and space and time rather than absolute nothingness? One approach to this question involves the anthropic principle, which says that we observe the universe to be the way it is because if it were significantly different, we wouldn't be here to observe it. This might seem like a circular argument, but it has some substance. The universe appears fine-tuned for life. Change the strength of gravity by even 1 part in 10 to the power of 35, and stars couldn't form. Change the strong nuclear force by a few percent, and atomic nuclei wouldn't be stable. Alter the electromagnetic force slightly, and chemistry as we know it would be impossible. The values of the fundamental constants fall within incredibly narrow ranges that allow for the existence of complex structures like atoms, molecules, stars, planets, and ultimately life. This fine-tuning has led some scientists to embrace the multiverse hypothesis. Maybe there are countless universes, each with different laws of physics and different values for the fundamental constants. In most of these universes, conditions don't allow for the development of complexity or life. But in a tiny fraction of them, the conditions happen to be right. We find ourselves in one of these rare universes simply because we couldn't exist anywhere else. This explanation doesn't require any fine-tuner or designer. It's just a selection effect. We observe a life-friendly universe because we're here to do the observing. But the multiverse hypothesis has serious problems. For one thing, it's extraordinarily difficult to test. If other universes exist, they're by definition beyond our ability to observe. We can't send probes there. We can't receive signals from them. Some physicists argue that this makes the multiverse idea unscientific, more philosophy than physics. Others counter that many accepted scientific ideas, like the interior of black holes or the state of the universe before the Big Bang, are also impossible to observe directly, yet we consider them legitimate subjects of scientific investigation. The multiverse comes in several varieties. The Level 1 multiverse, proposed by cosmologist Max Tegmark, arises simply from the infinite extension of space. If space is infinite and the distribution of matter is roughly uniform, then every possible arrangement of matter must occur somewhere. That means there are other regions of space, far beyond our observable horizon, where an exact copy of you is reading this exact script. There are regions where you made different choices, regions where dinosaurs never went extinct, regions with entirely different histories. This multiverse doesn't require any exotic physics. It follows naturally from the universe being infinite and homogeneous. The Level 2 multiverse arises from eternal inflation. According to inflationary cosmology, the early universe underwent a period of exponential expansion driven by a scalar field. In eternal inflation, this expansion never completely ends. Instead, it continues forever, with bubble universes like ours forming when inflation stops in local regions. Each bubble universe could have different physical laws and constants, determined by how the field settled into their final states. Our universe is just one bubble in an infinite foam of universes. The Level 3 multiverse is the many worlds interpretation of quantum mechanics, where every quantum measurement causes the universe to split into multiple branches. And the Level 4 multiverse is the most radical. It suggests that every mathematically consistent set of physical laws exists as an actual universe. All possible mathematical structures are real, and we inhabit just one of them. Critics of the multiverse point out what's called the measure problem. With infinitely many universes, how do you calculate probabilities? Any event that can happen will happen infinitely many times. Traditional probability theory breaks down. Some multiverse models predict that most conscious observers would be Boltzmann brains, random fluctuations in empty space that spontaneously assemble into brains with false memories, rather than evolved biological organisms in orderly universes. The fact that we're not Boltzmann brains suggests something is wrong with these models, but we don't know what. Despite these problems, the multiverse remains an active area of research. In September 2025, a paper on multiverse predictions for habitability examined how different assumptions about particle physics and cosmology affect the likelihood of observing our particular universe. The researchers found that certain combinations of theories make our universe more probable in a multiverse framework, while others make it highly improbable. These predictions could potentially be tested in future experiments, offering a way to either confirm or rule out the multiverse hypothesis. Let's turn to another deep mystery, the arrow of time. Why does time flow in only one direction? Why do we remember the past but not the future? Why do processes go one way, eggs breaking but never unbreaking, milk mixing into coffee but never unmixing? The fundamental laws of physics are time-symmetric. If you filmed a video of fundamental particles interacting and played it backward, you couldn't tell which direction was forward and which was backward. The equations work equally well in both directions. Yet our experience of time is anything but symmetric. The answer lies in the second law of thermodynamics, which states that entropy, or disorder, always increases in isolated systems. A broken egg has higher entropy than an intact egg. Mixed milk and coffee have higher entropy than separated milk and coffee. The universe started in an extremely low entropy state at the Big Bang, highly ordered and uniform. Since then, entropy has been increasing, and this increase defines the arrow of time. But this just pushes the question back one step. Why did the universe start with such low entropy? What set the initial conditions? Some cosmologists think the answer might involve the multiverse. In most possible universes, initial conditions would be random and high entropy. But only in low entropy universes could complex structures like stars, planets, and life emerge. Once again, we find ourselves in a special universe because we couldn't exist anywhere else. Other researchers are exploring more exotic ideas, like the possibility that the arrow of time emerges from quantum entanglement, or that time might flow differently in different parts of the multiverse, or even that time isn't fundamental at all but an emergent property of something deeper. Now let's consider the cosmic web, the large-scale structure of the universe. If you could zoom out far enough to see billions of light years at once, you'd see that galaxies aren't distributed randomly. They're arranged in an intricate pattern of filaments and voids, like a vast cosmic spider web. Superclusters of galaxies are connected by filaments of dark matter and gas, stretching hundreds of millions of light years across. Between the filaments are enormous voids, regions of space where almost no galaxies exist. This structure arose from tiny quantum fluctuations in the early universe, variations in density that were stretched to enormous sizes by cosmic inflation. In regions slightly denser than average, gravity pulled matter together, forming the first galaxies. In regions slightly less dense, matter flowed away, creating the voids. Over billions of years, this process sculpted the universe into the web-like structure we see today. Computer simulations of structure formation, using equations from general relativity and our understanding of dark matter and dark energy, can reproduce the observed cosmic web with remarkable accuracy. This is one of the great triumphs of modern cosmology. But mysteries remain. The distribution of galaxies shows unexpected patterns. There are correlations on scales so large that light hasn't had time to travel across them since the Big Bang. How did these regions know to line up in the same way? Some researchers have suggested that these correlations might be evidence of interactions between our universe and other universes in the multiverse, or remnants of physics from before the Big Bang. Others think they're just statistical flukes, unusual but not impossible random patterns. We need more data to decide. The origin of life is another profound mystery. How did non-living matter become alive? We know that life on Earth began at least 3.5 billion years ago, and possibly earlier. The oldest confirmed fossils are stromatolites, layered structures built by communities of microorganisms. But how did the first self-replicating molecules arise? How did simple chemicals organize themselves into the complex machinery of living cells? One popular theory is that life began in hydrothermal vents on the ocean floor, where hot mineral-rich water erupts from cracks in the Earth's crust. These vents provide energy and the right chemical environment for organic molecules to form. Experiments have shown that simple amino acids and nucleotides, the building blocks of proteins and DNA, can form under conditions similar to those in hydrothermal vents. But going from simple molecules to self-replicating systems is an enormous leap. The RNA world hypothesis suggests that early life was based on RNA rather than DNA. RNA can both store information like DNA and catalyze chemical reactions like proteins. Some researchers have managed to create self-replicating RNA molecules in the laboratory, but these are still far simpler than anything we'd call alive. The jump from chemistry to biology remains one of science's greatest unsolved problems. What makes the origin of life so mysterious is that it seems to require an unlikely series of events to occur in sequence. You need the right molecules to be in the right place at the right time. You need them to interact in just the right way to create more complex structures. You need some kind of containment, like a cell membrane, to keep the system together. And you need all of this to happen before the molecules degrade or disperse. The probability of all these steps occurring by chance seems vanishingly small. Yet life arose on Earth remarkably quickly. The planet formed 4.5 billion years ago, and it was initially a hellish place, bombarded by asteroids and volcanism, with an atmosphere toxic to modern life. It took perhaps 500 million years for the surface to cool enough for liquid water to exist. And then, almost immediately in geological terms, life appeared. This suggests that the origin of life might not be as improbable as we think, or that we're missing something important about how it happens. The discovery of extremophiles, organisms that thrive in extreme environments, has expanded our understanding of where life can exist. We've found microorganisms living in boiling hot springs, in freezing Antarctic ice, in highly acidic or alkaline conditions, deep underground where there's no sunlight, even in the reactor cores of nuclear power plants. Life is far more resilient and adaptable than we once believed. This raises the possibility that life might be common in the universe, even in environments we consider completely inhospitable. But if life is common, intelligence might not be. The evolution of complex multicellular life took billions of years on Earth. For most of its history, Earth was populated only by single-celled organisms. It wasn't until about 600 million years ago that complex multicellular life emerged in what's called the Cambrian explosion. Then it took another hundreds of millions of years for life to colonize land, for plants to spread, for animals to develop complex nervous systems and brains. Humans and our immediate ancestors have only existed for a few million years, a tiny fraction of Earth's history. Each step in this process might have required specific conditions that don't often occur together. Maybe Earth is unusually lucky, with the right kind of star, the right orbit, the right size moon to stabilize its rotation, the right amount of water, the right magnetic field to shield against radiation, the right tectonic activity to regulate carbon dioxide and maintain a stable climate. When you add up all these requirements, maybe life-bearing planets are common, but intelligent life is extraordinarily rare. Let's consider another cosmic enigma: gamma-ray bursts. These are the most violent explosions in the universe, releasing more energy in a few seconds than the Sun will emit in its entire 10 billion-year lifetime. For that brief moment, a gamma-ray burst can outshine every star in its galaxy combined. We detect them regularly from all over the sky, sometimes several per month. The longest gamma-ray bursts, lasting from a few seconds to several minutes, are thought to come from the collapse of massive stars into black holes. When a star at least 20 or 30 times more massive than the Sun exhausts its nuclear fuel, its core collapses catastrophically. If conditions are right, the collapse forms a rapidly spinning black hole surrounded by an accretion disk. Jets of matter and radiation are launched from the poles at nearly the speed of light. If Earth happens to lie in the path of one of these jets, we see a gamma-ray burst. Shorter bursts, lasting less than 2 seconds, likely come from the merger of two neutron stars or a neutron star and a black hole. When these ultra-dense objects spiral into each other, they release gravitational waves and produce a gamma-ray burst. In August 2017, astronomers witnessed such an event directly. The LIGO and Virgo gravitational wave detectors picked up the signal from two merging neutron stars. Less than 2 seconds later, gamma-ray telescopes detected a burst from the same location. This was the first time scientists had observed a cosmic event using both light and gravitational waves, inaugurating the era of multi-messenger astronomy. If a gamma ray burst occurred in our galaxy and was aimed at Earth, it would be catastrophic. The intense radiation would strip away the ozone layer, exposing the surface to harmful ultraviolet radiation from the sun. It could trigger mass extinctions. Some researchers have speculated that past extinction events might have been caused by nearby gamma ray bursts, though there's no definitive evidence for this. The good news is that gamma ray bursts are rare, and the odds of one occurring close enough and aimed directly at us are extremely low. Another mystery involves fast radio bursts, intense pulses of radio waves that last for milliseconds. They were first discovered in 2007, and for years, astronomers debated whether they were even real or just instrumental artifacts. But they are real, and they're coming from billions of light years away. The energy required to produce a detectable signal at such distances is staggering. In a few milliseconds, these events release as much energy as the sun emits in several days. For a while, nobody knew what caused fast radio bursts. Theories ranged from colliding neutron stars to evaporating black holes to alien civilizations. In April 2020, astronomers finally traced a fast radio burst to its source, a magnetar, a neutron star with an extraordinarily strong magnetic field. Magnetars are formed when massive stars collapse, and their magnetic fields can be trillions of times stronger than Earth's. Somehow, these intense magnetic fields produce the radio bursts, though the exact mechanism is still unclear. Fast radio bursts have become useful tools for studying the universe. As their radio waves travel through space, they interact with electrons in the intergalactic medium, the diffuse gas between galaxies. By analyzing how the radio signal is dispersed, astronomers can map the distribution of matter along the line of sight. This helps us understand the cosmic web and test cosmological models. Then there's the mystery of cosmic rays, high-energy particles from space that constantly bombard Earth. Most cosmic rays are protons, atomic nuclei stripped of their electrons, traveling at nearly the speed of light. Some cosmic rays have energy so high that they shouldn't even exist according to theoretical limits. The most energetic cosmic ray ever detected, called the Oh My God particle, had an energy of about 300 billion electron volts. That's roughly the kinetic energy of a baseball thrown at 60 miles per hour, but concentrated in a single atomic nucleus. Where do these ultra-high energy cosmic rays come from? They can't come from our galaxy because they would lose energy interacting with the cosmic microwave background radiation. They must come from extragalactic sources. But what? Supernova remnants can accelerate particles to high energies, but probably not high enough. Active galactic nuclei, powered by supermassive black holes, are strong candidates. A recent study from Norwegian University of Science and Technology suggests that winds from supermassive black holes, moving at half the speed of light, might accelerate particles to the extreme energies observed in cosmic rays. The composition of cosmic rays also tells us about nucleosynthesis in the universe. By measuring the relative abundances of different elements, we can learn about the nuclear processes occurring in stars and supernovae. Cosmic rays are like messengers from distant parts of the galaxy, carrying information about conditions we can't observe any other way. Another frontier in physics is the search for quantum gravity, a theory that would unify quantum mechanics and general relativity. These two pillars of modern physics are extraordinarily successful in their respective domains. Quantum mechanics describes the behavior of particles and forces at the smallest scales. General relativity describes gravity and the large-scale structure of spacetime. But they're fundamentally incompatible. Quantum mechanics treats time as absolute and fixed. General relativity treats time as flexible and intertwined with space. Quantum mechanics deals with probabilities and uncertainties. General relativity is deterministic. When you try to apply both theories to the same situation, like the interior of a black hole or the first moments of the Big Bang, you get nonsensical results. String theory is one attempt to resolve this conflict. It proposes that the fundamental constituents of the universe aren't point-like particles, but tiny vibrating strings. Different vibration modes of these strings correspond to different particles. Gravity emerges naturally from string theory, which is why physicists find it so promising. But string theory requires extra dimensions of space beyond the three we experience. These extra dimensions are supposedly curled up so small that we can't detect them directly. The problem with string theory is that it makes few testable predictions. There are countless possible ways the extra dimensions could be configured, leading to a vast landscape of possible universes. Some physicists argue that this makes string theory unfalsifiable and therefore unscientific. Others maintain that string theory is the only viable candidate for a quantum theory of gravity and that we need to be patient while the mathematical framework is developed further. Loop quantum gravity is an alternative approach that doesn't require extra dimensions. It treats space-time itself as quantized, made up of discrete chunks rather than being continuous. At the smallest scales, space becomes a network of interconnected loops, and area and volume can only take certain discrete values. This solves some problems but creates others, and it's not yet clear whether loop quantum gravity can make testable predictions. A third approach, called emergent gravity, suggests that gravity isn't a fundamental force at all but an emergent phenomenon, like temperature or pressure. Just as temperature emerges from the average motion of molecules, gravity might emerge from more fundamental quantum processes. This idea is highly speculative but has gained attention in recent years. We also need to talk about the universe's expansion rate, a mystery that has cosmologists baffled and wondering if our understanding of the cosmos needs a major revision. When astronomers measure how fast the universe is expanding, they get different answers depending on how they measure it. Measurements based on the cosmic microwave background radiation, the afterglow of the Big Bang, give one value for the expansion rate, known as the Hubble constant. But measurements based on observations of nearby galaxies and type Ia supernovae give a different, significantly higher value. This discrepancy, called the Hubble tension, shouldn't exist if our understanding of the universe is correct. At first, cosmologists thought the tension would go away as measurements became more precise. But the opposite has happened. As observations have improved, the discrepancy has become more pronounced and statistically significant. Either there's some systematic error we haven't identified in one or both methods, or our standard model of cosmology is missing something important. Maybe dark energy isn't constant but changes over time. Maybe there's an unknown form of matter or energy. Maybe the laws of physics were different in the early universe. Maybe we need to modify general relativity. The Hubble tension is forcing cosmologists to reconsider fundamental assumptions. Some researchers are exploring models where the early universe underwent multiple phases of expansion at different rates. Others are investigating whether variations in the strength of dark energy over time could explain the observations. Still others think we might need entirely new physics, something beyond the standard model of cosmology. There's also the horizon problem, which inflation was invented to solve but which still poses questions. When we look at the cosmic microwave background, we see that temperature variations are incredibly uniform across the entire sky. Regions of space that are now on opposite sides of the observable universe, separated by 90 billion light-years, have almost identical temperatures. But according to standard Big Bang cosmology, these regions were never in causal contact. Light hasn't had time since the Big Bang to travel between them. So how did they equilibrate to the same temperature? Cosmic inflation solves this by proposing that the universe underwent a brief period of exponential expansion in its first fraction of a second. During inflation, a tiny region of space, small enough for different parts to be in thermal contact, expanded to become larger than our observable universe. This explains why distant regions have the same temperature. They started out close together. But what caused inflation to start? What caused it to stop? What was the universe like before inflation? These questions remain unanswered. Some cosmologists have proposed alternatives to inflation. The cyclic model suggests that the universe goes through infinite cycles of expansion and contraction, with each Big Bang followed eventually by a big crunch that leads to another Big Bang. In this model, there is no beginning and no end, just an eternal cosmic cycle. Another idea is the ekpyrotic universe, where our universe is a three-dimensional membrane floating in a higher dimensional space. Occasionally, our brain collides with another brain, and this collision produces what we perceive as the Big Bang. The nature of space-time itself is a mystery. Is it continuous or discrete? Is it fundamental or emergent? Some physicists think space-time emerges from more basic quantum information. In this view, space and time aren't the stage on which physics happens. They're part of the story, arising from the entanglement and interaction of quantum bits of information. If this is true, then at the Planck scale, about 10 to the power of minus 35 meters, space-time as we know it breaks down and is replaced by some more fundamental quantum structure. Recent research in quantum gravity has explored the idea that space-time might be holographic. The holographic principle states that all the information contained in a volume of space can be encoded on the boundary of that volume, like a hologram encoding a three-dimensional image on a two-dimensional surface. This principle emerged from studies of black holes, where Stephen Hawking and Jacob Bekenstein showed that a black hole's entropy is proportional to its surface area rather than its volume. If space-time is holographic, then our three-dimensional universe might be a projection of information encoded on a distant two-dimensional surface. Another layer of mystery involves antimatter. For every type of particle, there exists an antiparticle with the same mass but opposite charge. When a particle and its antiparticle meet, they annihilate, converting their mass into pure energy. In the Big Bang, matter and antimatter should have been created in equal amounts, and they should have annihilated each other almost immediately, leaving a universe filled with nothing but radiation. Yet here we are, made of matter, living in a universe filled with matter galaxies and matter stars. What happened to all the antimatter? The answer is that there must have been a slight asymmetry in the laws of physics, favoring matter over antimatter by about 1 part in a billion. For every billion antimatter particles, there were 1,000,000,001 matter particles. After the matter-antimatter annihilation, only that tiny excess of matter survived. Everything we can see, every atom in every star, planet, and living thing, comes from that 1 in a billion surplus. But what caused the asymmetry? This question led to the discovery of charge parity violation. The fact that certain physical processes behave slightly differently when you swap particles for antiparticles and flip their spatial coordinates. The weak nuclear force violates CP symmetry, which could explain the matter-antimatter asymmetry, but calculations show that the amount of CP violation in the standard model of particle physics is too small. There must be additional sources we haven't discovered yet. Neutrino experiments are searching for clues. In October 2025, the T2K experiment in Japan and the NOVA experiment in the United States combined their data to achieve unprecedented precision in studying neutrinos. These ghostly particles barely interact with matter and come in 3 types, or flavors. Neutrinos can oscillate between flavors as they travel, and the pattern of oscillations might be different for neutrinos and antineutrinos. If so, this could be the source of the matter-antimatter asymmetry. The experiments are looking for subtle differences in how neutrinos and antineutrinos behave, differences that could explain why we exist. Neutrinos themselves are mysterious. For decades, scientists thought they were massless, but experiments in the late 1990s showed that neutrinos have a tiny mass, much smaller than any other fundamental particle. We don't know why their mass is so small or what determines its value. Neutrinos might also be their own antiparticles, a unique property that could have profound implications for understanding the early universe. Then there's the question of vacuum stability. The Higgs field, which gives particles their mass, exists in a particular state called a vacuum expectation value. But quantum calculations suggest that the Higgs field might not be in its lowest possible energy state. It could be in a false vacuum, a metastable state that's locally stable but not globally stable. If the Higgs field were to quantum tunnel to a lower energy state, a bubble of true vacuum would form and expand at the speed of light, destroying everything in its path. The laws of physics inside the bubble would be different. and the universe as we know it would cease to exist. Before you panic, the calculations suggest that if this is going to happen, it won't be for many billions or trillions of years, far longer than the current age of the universe. But the fact that it's possible at all is unsettling. Our universe might be fundamentally unstable, existing temporarily in a state that will eventually decay. Some physicists think that measurements of the top quark mass and the Higgs boson mass suggest we're right on the edge between stability and instability, a situation that seems too coincidental to be accidental. Let's consider the nature of time itself, one of the deepest and most confusing aspects of reality. Is time fundamental, or does it emerge from something more basic? Does time have a beginning? Will it have an end? Does time even flow, or is that just an illusion created by our consciousness? According to general relativity, time is part of space-time, a four-dimensional structure where past, present, and future all exist simultaneously. There's no privileged moment called now. Your past self, your present self, and your future self all exist equally in the four-dimensional space-time manifold. From this perspective, sometimes called the block universe or eternalism, the passage of time is an illusion. Everything that ever happened or ever will happen is already laid out in the space-time continuum. Yet our experience tells us that time does flow. We remember the past, experience the present, and anticipate the future. Events happen in sequence. This subjective flow of time seems undeniable. Some physicists think that the flow of time emerges from the increase of entropy, from the second law of thermodynamics. Others think it's related to the expansion of the universe or to quantum decoherence, the process by which quantum systems become classical. Still others believe that consciousness itself creates the flow of time, that the subjective experience of temporal passage is fundamental and can't be reduced to physics. Time travel adds another layer of paradoxes. General relativity allows for solutions where closed time-like curves exist, paths through space-time that loop back on themselves, allowing travel to the past. If you could travel backward in time and prevent your own birth, you create a logical contradiction. One resolution is the Novikov self-consistency principle, which states that if time travel is possible, any actions you take in the past must be consistent with the history you remember. You can't change the past because you were already part of it. Another resolution is the many worlds interpretation. When you travel back in time and change something, you create a new branch of the multiverse. You don't change your own past. You create an alternative timeline. In your original timeline, you still existed and traveled back in time. In the new timeline, maybe you were never born, but that doesn't create a paradox because they're separate realities. Whether time travel is actually possible remains an open question. The energy requirements are enormous, possibly requiring exotic matter with negative energy density. And there are theoretical reasons to think that quantum effects might prevent the formation of closed time-like curves. Stephen Hawking proposed the chronology protection conjecture, the idea that the laws of physics conspire to prevent time travel and preserve causality. But we don't have a final theory of quantum gravity, so we can't say for certain. There's also the mystery of quasars and active galactic nuclei, among the most energetic and luminous objects in the universe. A quasar can outshine an entire galaxy of hundreds of billions of stars, all from a region no larger than our solar system. This tremendous energy output comes from a supermassive black hole at the galaxy's center, accreting matter at a furious rate. As matter spirals into the black hole, it forms an accretion disk that heats to millions of degrees, emitting vast amounts of radiation across the electromagnetic spectrum. Some quasars produce jets that shoot out from the poles of the black hole at nearly the speed of light, extending for millions of light years into space. The mechanism that creates these jets is still not fully understood. They involve complex interactions between the black hole's rotation, the magnetic fields in the accretion disk, and the properties of the infalling matter. When one of these jets happens to point toward Earth, we see a blazar, an extremely bright and variable source of gamma rays and other high-energy radiation. The study of quasars has revealed how galaxies and their central black holes co-evolve. There seems to be a tight relationship between the mass of a galaxy's supermassive black hole and the properties of the galaxy itself, particularly the mass of its central bulge. Somehow, the black hole and the galaxy regulate each other's growth through feedback processes that are still being investigated. Observations of the most distant quasars, those from when the universe was less than 1 billion years old, have revealed a puzzle. These quasars contain supermassive black holes with masses of billions of suns. How did these black holes grow so large so quickly? In the standard picture, black holes grow by accreting matter over time, but there simply hasn't been enough time for them to reach such enormous masses. Either black holes formed much larger than we thought in the early universe, perhaps from the direct collapse of massive gas clouds, or they grew much faster than current models predict, or both. Recent observations with the James Webb Space Telescope have found evidence for overmassive black holes in the early universe, black holes that are more massive than expected based on the size of their host galaxies. This challenges our understanding of how galaxies and black holes form and evolve. Some researchers suggest that these black holes might have formed through a process called direct collapse, where massive clouds of gas collapse directly into black holes without forming stars first. This could create black holes with masses of tens of thousands or even hundreds of thousands of solar masses right from the start, giving them a head start on growth. Gravitational waves offer a new window into these extreme cosmic events. Since the first detection of gravitational waves in 2015 from merging black holes, the LIGO, Virgo, and CAGRA detectors have observed dozens of events. Each detection provides information about the masses and spins of the merging objects, testing our understanding of general relativity in the strong field regime where gravity is incredibly intense. In December 2025, researchers achieved one of the clearest gravitational wave signals ever recorded, designated GW250114. This detection confirmed two major predictions: Hawking's area theorem, which states that the total area of a black hole's event horizon can never decrease, and the ring-down behavior predicted by general relativity. When two black holes merge, the resulting black hole is initially distorted and oscillates, ringing like a bell. These oscillations, called quasi-normal modes, are predicted precisely by general relativity, and the observations match the predictions perfectly. Future gravitational wave detectors, like the space-based LISA mission plan for launch in the mid-2030s, will detect waves from supermassive black hole mergers, events that release more energy in gravitational waves than the entire visible universe emits in light. LISA will also detect waves from extreme mass ratio in spirals, where a stellar mass object spirals into a supermassive black hole, mapping out the spacetime around the black hole with exquisite precision. One of the strangest predictions of general relativity is the existence of naked singularities, singularities that aren't hidden behind event horizons. Roger Penrose proposed the cosmic censorship conjecture, which states that singularities always form inside black holes where they can't be observed from the outside. If naked singularities could exist, they would create problems for physics because they're regions where our equations break down and predictability is lost. Most physicists believe cosmic censorship is true, but it's never been proven mathematically, and some solutions to Einstein's equations do seem to allow naked singularities under very specific conditions. Extra dimensions, if they exist, would revolutionize physics. In October 2025, Professor Dieter Lust and collaborators published a study suggesting that our universe might contain two extra spatial dimensions, each about 1 micron in size. These hidden dimensions could help explain two major puzzles: the hierarchy problem, which asks why the energy scale of particle physics is so much smaller than the Planck scale, and the cosmological constant problem, which asks why the vacuum energy of the universe is so extraordinarily small. If these micron-sized dimensions exist, they might be testable in experiments within the next few years. The theory predicts that gravity becomes stronger at very small distances, and precision measurements of gravitational forces at the micron scale could detect this effect. It would be one of the most important experimental confirmations in physics, revealing that our universe has more dimensions than we can see. The theory also offers a way to understand dark matter. In models with extra dimensions, particles can move through the extra dimensions, creating what are called Kaluza-Klein particles. These particles would be heavier than ordinary particles due to their motion in the extra dimensions, and they could be stable, making them viable dark matter candidates. Think about the implications. If extra dimensions exist, then the universe has a hidden structure that we've never perceived directly. Everything we've ever observed, every experiment we've ever conducted, has been confined to our three spatial dimensions. But particles and forces might be able to access these extra dimensions, influencing our world in subtle ways we've attributed to dark matter or quantum weirdness. The possibility of life beyond Earth remains one of the most profound open questions. The discovery of thousands of exoplanets has shown that planetary systems are common. Many stars have planets in the habitable zone where liquid water could exist. Some of these planets are rocky like Earth, with similar sizes and compositions. If life arose on Earth, why wouldn't it arise on other worlds with similar conditions? But the more we learn about Earth's history, the more we realize how many fortunate accidents were involved in creating a planet suitable for complex life. Earth has a large moon that stabilizes its axial tilt, preventing extreme climate swings. It has plate tectonics that cycle carbon dioxide and maintain a stable climate over geological timescales. It has a magnetic field generated by a liquid iron core that shields the surface from harmful solar and cosmic radiation. It's located in a quiet region of the galaxy, away from the densest parts where supernovae and gamma-ray bursts are more common. Jupiter acts as a cosmic vacuum cleaner, its immense gravity deflecting or capturing asteroids and comets that might otherwise bombard the inner solar system. Without Jupiter, Earth might experience catastrophic impacts far more frequently. All these factors combined create a stable environment where life can evolve over billions of years. Maybe Earth-like planets are common, but planets with all these additional favorable conditions are rare. The search for biosignatures, signs of life in the atmospheres of exoplanets, is one of the most exciting areas of current astronomy. The James Webb Space Telescope and future missions will analyze starlight filtering through exoplanet atmospheres, looking for molecules like oxygen, methane, and water vapor in combinations that suggest biological activity. Finding definitive biosignatures would be one of the greatest discoveries in human history, proof that we're not alone. But we must be cautious about false positives. Some molecules can be produced by geological processes as well as biological ones. Methane, for instance, can come from volcanoes or chemical reactions in a planet's crust. Oxygen can be produced by the breakdown of water molecules in the upper atmosphere. We'll need to look for combinations of gases that are difficult to explain without biology. And even then, we'll need to be careful about jumping to conclusions. The possibility of finding life in our own solar system is tantalizing. Mars probably had liquid water on its surface billions of years ago, with rivers, lakes, and perhaps even oceans. Did life arise during that wetter period? And if it did, might some of it survive today in underground aquifers or ice deposits? NASA's Perseverance rover is currently collecting samples that will eventually be returned to Earth for detailed analysis. These samples could contain fossilized microorganisms or chemical traces of ancient Martian life. The icy moons of Jupiter and Saturn are even more promising. Europa, one of Jupiter's moons, has an ocean of liquid water beneath its icy crust, kept warm by tidal heating from Jupiter's gravity. The ocean could be tens of kilometers deep and might contain more water than all of Earth's oceans combined. Enceladus, a moon of Saturn, also has a subsurface ocean and actually sprays plumes of water into space from geysers at its south pole. Spacecraft have flown through these plumes and detected organic molecules, the building blocks of life. Future missions will explore these moons more thoroughly. NASA's Europa Clipper, launched in October 2024, will conduct detailed reconnaissance of Europa, studying its ice shell, its ocean, and searching for locations where the ocean might be close to the surface or even exposed. If life exists in Europa's ocean, it would have evolved independently of life on Earth, providing a second example of abiogenesis and helping us understand how common life really is in the universe. Imagine if we found life in multiple locations in our own solar system. That would suggest that life arises readily wherever conditions are right, implying that the universe is probably teeming with life. But if we explore Mars, Europa, Enceladus, and other promising locations and find nothing, that would suggest life is extraordinarily rare, and we might be alone in the galaxy or even the observable universe. What about the ultimate question? What is the fate of the universe? Will it expand forever, growing colder and darker until the last stars burn out and black holes evaporate? Will it eventually collapse back on itself in a big crunch? Or could something even stranger happen? Current observations suggest that the universe will continue expanding forever, driven by dark energy. In this scenario, called the Big Freeze or heat death, the universe will become increasingly dilute and cold. Star formation will cease as gas clouds are used up. Existing stars will exhaust their fuel and die. Galaxies will dim as more and more stars become white dwarfs, neutron stars, and black holes. Eventually, even black holes will evaporate through Hawking radiation, though this will take an incomprehensibly long time, something like 10 to the power of 100 years for the largest supermassive black holes. In the final state, the universe will be filled with a dilute soup of elementary particles, photons, and gravitons, growing ever more dispersed as space continues to expand. The temperature will approach absolute zero. No structures will exist, no life, no thought, no memory of the civilizations that once flourished when the universe was young and warm and full of light. It's a bleak fate, but it's billions of years in the future, so far away that it's almost impossible to comprehend. But dark energy might not remain constant. If it changes over time, the universe's fate could be different. If dark energy increases, we might face a big rip, where the accelerating expansion becomes so extreme that it tears apart galaxies, stars, planets, and eventually atoms themselves. In this scenario, the universe ends not in cold darkness but in violent disintegration. Alternatively, if dark energy decreases or becomes negative, the expansion could slow down and reverse, leading to a big crunch where everything collapses back into a hot, dense state. Some cyclic models propose that the Big Crunch could lead to a new Big Bang, restarting the cosmic cycle. In these models, the universe has no beginning and no end, just an eternal sequence of expansions and contractions. Or perhaps the vacuum decay scenario will play out, where a bubble of true vacuum nucleates somewhere in the universe and expands at the speed of light, transforming the laws of physics as it goes. From inside the bubble, the change would be instantaneous and final. We wouldn't see it coming. One moment the universe exists as we know it, and the next moment everything changes. These speculations about the far future depend on physics we don't fully understand. We don't know what dark energy is or how it behaves over time. We don't know if our current understanding of quantum mechanics and general relativity is complete or if there are deeper theories waiting to be discovered. We don't know if the laws of physics are eternal or if they can change. Every prediction about the ultimate fate of the universe is provisional, subject to revision as we learn more. But that uncertainty is part of what makes science so exciting. We live in a time when fundamental questions about reality are being actively investigated. New telescopes, new detectors, new experiments are pushing the boundaries of what we know. The James Webb Space Telescope is peering back to the first galaxies that formed after the Big Bang. Gravitational wave detectors are listening to the whispers of merging black holes. Particle accelerators are searching for new fundamental particles and forces. Quantum computers are beginning to explore the strange landscape of quantum mechanics in ways that were impossible before. And through all of this, we're forced to confront the deepest mystery of all. Why are we here to ask these questions? In a universe governed by physical laws, where did consciousness come from? How did matter organize itself into brains capable of contemplating their own existence? How did the universe become aware of itself? Some researchers think consciousness is just what information processing feels like from the inside. When a system reaches a certain level of complexity and integrates information in the right way, subjective experience emerges. This is the basis of theories like integrated information theory, which tries to quantify consciousness mathematically. Other researchers think consciousness requires quantum processes, that the strange rules of quantum mechanics are somehow essential to generating subjective experience. But maybe consciousness is even more fundamental than that. Maybe the universe itself is in some sense conscious, with human consciousness being a localized manifestation of a universal field of awareness. This sounds mystical, but recent theoretical papers have explored this idea using the mathematical framework of quantum field theory. If consciousness is a fundamental field like electromagnetism or gravity, then it's been present throughout the universe's entire history, not something that emerged only recently with biological brains. These ideas remain highly speculative, but they're forcing scientists to take seriously questions that were once considered purely philosophical. The nature of consciousness, the relationship between mind and matter, the role of the observer in quantum mechanics, these aren't just abstract puzzles. They're intimately connected to the deepest questions about what the universe is and why it exists. As we stand here, contemplating these 30 mysteries, we must confront a humbling truth. We don't understand the vast majority of the universe we inhabit. We've discovered dark matter and dark energy, but we don't know what they are. We've observed the accelerating expansion of the universe, but we don't know what's driving it. We've found evidence for quantum entanglement, but we don't know what it means. We've detected gravitational waves from merging black holes, but we don't know what happens at singularities. We've seen the fine-tuning of physical constants, but we don't know why they have the values they do. We've experienced consciousness, but we don't know how it arises or what it's made of. Think about what this means. Every answer we find opens up new questions. Every mystery we solve reveals deeper mysteries underneath. The more we learn, the more we realize how little we know. This could be discouraging, but instead, it should fill you with wonder. We live in a universe that's far stranger, far more complex, far more mysterious than our ancestors ever imagined. And we've only just begun to explore it. The universe doesn't owe us answers. It doesn't care whether we understand it or not. But somehow, against all odds, collections of atoms have organized themselves into beings capable of asking these questions. Beings who can look out at the cosmos and try to comprehend what they see. We are the universe attempting to understand itself. Conscious matter investigating its own origins and fate. So when you look up at the night sky, remember that you're seeing only a tiny fraction of what's really there. Behind the visible stars lies an invisible scaffolding of dark matter, holding galaxies together with gravitational forces we can measure but not explain. Between the galaxies stretches dark energy, pushing space apart, accelerating the cosmic expansion toward an uncertain future. And somewhere in the quantum foam, in the fabric of space-time itself, might lie the answers to questions we haven't even learned to ask yet. We stand at a threshold, equipped with instruments and theories powerful enough to probe the deepest mysteries of existence. What we discover in the coming decades could transform our understanding of reality as profoundly as quantum mechanics and relativity did in the 20th century. Or we might find that some questions are beyond our ability to answer, that the universe keeps its deepest secrets hidden behind horizons we can never cross. But even if we never solve all these mysteries, the quest to understand them defines us as a species. We are the ones who ask why, who refuse to accept the universe at face value, who insist on knowing how things work and what it all means. That drive to understand, that insatiable curiosity, is perhaps the most mysterious thing of all, the strangest fact about this strange universe we inhabit. The 30 deepest mysteries of the universe aren't just scientific problems waiting to be solved. They're invitations to wonder, reminders that reality is far richer and more complex than common sense suggests. They challenge us to think bigger, to question assumptions, to imagine possibilities that seem impossible. And in that sense, these mysteries are gifts, keeping us humble in the face of cosmic immensity, keeping us curious about what lies beyond the next horizon. As you go about your day, remember that you're surrounded by mysteries. Neutrinos are passing through you. Quantum fields are fluctuating in the vacuum. Dark matter is influencing the motion of the galaxy you're traveling through. Time is flowing forward, or perhaps just seeming to flow, while the past and future exist timelessly in the four-dimensional space-time manifold. Your consciousness is emerging from quantum processes in your brain, or perhaps tapping into a universal field of awareness that permeates all of space. These aren't abstractions. This is your reality, the universe you actually inhabit. And the deepest mystery of all might be this. In a cosmos so vast, so ancient, so filled with incomprehensible forces and invisible substances, you exist. You're here now, aware of it all, asking questions that the universe itself seems to have no obligation to answer. But we're not done yet. There are more mysteries that demand our attention, more questions that pull at the fabric of everything we think we understand. Let's dive deeper into the enigmas that haunt the edges of physics and cosmology, the problems that keep scientists awake at night, wondering if we'll ever find answers. Consider the mystery of magnetic fields in the universe. Galaxies, stars, planets, even the vast spaces between galaxies, are threaded with magnetic fields. But where did these fields come from? In the early universe, just after the Big Bang, there shouldn't have been any magnetic fields. The cosmos was a hot, dense soup of particles and radiation, too chaotic for organized magnetic structures to form. Yet today, magnetic fields are everywhere, and some of them are incredibly strong. The Earth's magnetic field protects us from the solar wind and cosmic radiation, creating the beautiful auroras near the poles. The Sun's magnetic field drives solar flares and coronal mass ejections, violent eruptions that can disrupt satellites and power grids on Earth. Neutron stars called magnetars have magnetic fields trillions of times stronger than anything we can create in laboratories. These fields are so intense that they warp the very atoms in the neutron star's crust, creating stresses that occasionally cause the star to crack, releasing bursts of gamma rays that we detect from across the galaxy. But how did these magnetic fields originate? One theory is that they were created by turbulence in the early universe, random motions in the plasma that created small seed magnetic fields. These seeds were then amplified over billions of years by the motion of conducting fluids in stars and planets, a process called the dynamo effect. But calculations suggest that the seed fields would have been incredibly weak, and it's not clear whether the dynamo mechanism could amplify them enough to explain what we see today. Another puzzle involves the rotation curves of galaxies, the data that originally revealed dark matter. When astronomers measure how fast stars and gas orbit around the centers of galaxies, they find something peculiar. In our models, the rotation speed should decrease with distance from the galactic center. But instead, the rotation curves flatten out, staying constant even at the outermost edges of galaxies. This is the signature of dark matter halos, vast spherical distributions of invisible matter surrounding galaxies. But the dark matter halos themselves are mysterious. They seem to have a specific structure, with the density decreasing smoothly from the center outward. Computer simulations of dark matter predict something different. They predict that dark matter should clump into many small subhalos, creating a much more granular structure. This is called the missing satellites problem. Where are all the small dark matter clumps that simulations predict should exist? Some researchers think the problem lies in our understanding of star formation. Maybe small dark matter halos exist, but most of them never form stars, remaining dark and invisible. Others think the simulations are missing important physics, or that dark matter interacts with itself in ways we haven't accounted for. Still others suggest that dark matter doesn't exist at all, and what we're seeing is a modification of gravity on large scales. This idea, called modified Newtonian dynamics or MOND, has had some success in explaining galaxy rotation curves, but it struggles to explain other observations like gravitational lensing and the cosmic microwave background. The cosmic microwave background itself contains mysteries within mysteries. This radiation, the afterglow of the Big Bang, has been mapped in exquisite detail by satellites like WMAP and Planck. The temperature variations are incredibly small, just a few hundred thousandths of a degree, but they tell us about the universe when it was only 380,000 years old. The pattern of hot and cold spots encodes information about the geometry of space, the amount of dark matter and dark energy, the density of ordinary matter, and much more. But there are anomalies. One is called the cold spot, a region of the CMB that's colder and larger than statistical fluctuations would predict. Some researchers think it might be a supervoid, an enormous region of space with less matter than average, causing the CMB photons passing through it to lose energy. Others have speculated it could be evidence of a collision with another universe in the multiverse, though this is highly controversial. There's also the axis of evil, a strange alignment of the largest scale temperature fluctuations in the CMB. These fluctuations seem to point in a preferred direction in space, which shouldn't happen if the universe is homogeneous and isotropic as the standard cosmological model assumes. It might be a statistical fluke, or it might be telling us something important about the geometry or topology of the universe. Maybe space is curved in ways we haven't accounted for, or maybe the universe has a more complex shape than we think. The question of the universe's topology is fascinating. We usually assume the universe is flat and infinite, but it could be curved and finite. Imagine a universe shaped like a three-dimensional torus, a donut shape. If you traveled far enough in one direction, you'd end up back where you started, just like traveling around the Earth's surface. In such a universe, we might see multiple images of the same galaxies, light having traveled around the universe from different directions. Astronomers have searched for these repeated patterns in galaxy surveys, but they haven't found any convincing evidence. Either the universe is too large for light to have circled it yet, or it really is infinite after all. Then there's the lithium problem. When astronomers measure the abundance of lithium in the oldest stars, they find much less than the Big Bang nucleosynthesis models predict. In the first few minutes after the Big Bang, when the universe was hot and dense enough for nuclear reactions to occur, light elements like hydrogen, helium, and lithium were created. The amounts of each element depend on the density of ordinary matter and the expansion rate of the early universe. The predictions for hydrogen and helium match observations perfectly, but lithium is off by a factor of 3 or 4. The oldest stars have only about a third as much lithium as they should. Why? Some astronomers think lithium was destroyed inside stars by nuclear reactions and convection currents that mixed it down into hotter regions where it burned up. Others think there's something wrong with our models of stellar evolution or our understanding of Big Bang nucleosynthesis. Still others have suggested more exotic explanations, like the decay of hypothetical dark matter particles in the early universe, which could have altered the lithium abundance. The mystery of reionization is another chapter in the universe's history that we're still trying to understand. After the cosmic microwave background was emitted, when the universe was 380,000 years old, space was filled with neutral hydrogen atoms. These atoms absorbed ultraviolet light, making the universe opaque to certain wavelengths. Then, sometime between a few 100 million years and a billion years after the Big Bang, something changed. The neutral hydrogen became ionized again, its electrons stripped away, making space transparent. What caused reionization? The most likely culprit is the first generation of stars, massive luminous stars that formed from pristine hydrogen and helium, without any heavier elements. These stars would have been hot and bright, emitting intense ultraviolet radiation that could ionize the surrounding hydrogen. But we don't know exactly when the first stars formed, how massive they were, or how many of them there were. The James Webb Space Telescope is now peering back to this epoch, finding galaxies that existed when the universe was just a few 100 million years old, helping us piece together the story of reionization. And speaking of the early universe, what about cosmic inflation itself? While inflation solves many problems in cosmology, it raises new questions. What caused inflation to start? What was the universe like before inflation? And most mysteriously, what is the inflating field, the hypothetical field that drove the exponential expansion? Some versions of inflation predict that the expansion never truly ends globally, leading to eternal inflation. In this scenario, different regions of space stop inflating at different times, creating bubble universes with potentially different physical properties. Our observable universe is just one bubble in an eternally inflating multiverse. This sounds speculative, but it falls naturally out of many inflation models. If eternal inflation is correct, then the multiverse isn't just a possibility. It's an inevitable consequence of the physics that explains our own universe's initial conditions. But can we test inflation? Astronomers are looking for primordial gravitational waves, ripples in space-time created during the inflationary epoch. These gravitational waves would have left an imprint on the cosmic microwave background, creating a specific pattern in the polarization of the light. Detecting this signal would provide strong evidence for inflation and tell us about the energy scale at which it occurred. Several experiments, including ground-based telescopes in Antarctica and space missions in development, are searching for this signature. Let's talk about the hierarchy problem in particle physics. The Higgs boson, discovered at the Large Hadron Collider in 2012, has a mass of about 125 gigaelectronvolts. This is extraordinarily small compared to the Planck mass, the natural mass scale set by quantum gravity, which is about 10 to the power of 19 gigaelectronvolts. Why is there such a huge gap between these scales? In quantum field theory, the Higgs mass should receive enormous corrections from virtual particles, pushing it up to the Planck scale. The fact that it's so much smaller suggests that something is canceling out these corrections with incredible precision. One solution is supersymmetry, a theory that proposes every known particle has a heavier superpartner. These superpartners would contribute corrections that exactly cancel those from ordinary particles, naturally keeping the Higgs mass small. But despite extensive searches at the LHC and other experiments, no supersymmetric particles have been found. If supersymmetry exists, the superpartners must be heavier than originally thought, which makes the theory less natural and elegant. Some physicists are losing faith in supersymmetry, while others maintain that we just need more powerful particle accelerators to find the superpartners. Another proposed solution is that the Higgs boson is not a fundamental particle but a composite object made of more fundamental constituents, similar to how protons are made of quarks. In these theories, called technicolor or composite Higgs models, the Higgs mass is small because it's determined by the strong interactions that bind the constituents together, not by the Planck scale. But these models have their own problems and haven't been confirmed experimentally. The strong CP problem is yet another mystery in particle physics. The equations of quantum chromodynamics, the theory of the strong nuclear force, allow for a term that would violate CP symmetry, meaning the equations would look different if you swap particles for antiparticles and flip spatial coordinates. The strength of this CP violating term is controlled by a parameter called theta. Experimental measurements show that theta is incredibly small, less than 10 to the power of minus 10. But there's no reason in the theory for theta to be so small. It could have any value from 0 to 1. Why is it so close to 0? This is the strong CP problem. One proposed solution is the axion, a hypothetical particle that dynamically adjusts the value of theta to be 0. Axions would be very light and weakly interacting, making them excellent dark matter candidates. Experiments like ADMX are searching for axions, and if they're found, they would solve two major mysteries at once: the strong CP problem and the nature of dark matter. The origin and nature of cosmic magnetic fields connects to the mystery of cosmic rays, those high-energy particles bombarding Earth from space. We know that supernova remnants can accelerate particles to high energies through a process called shock acceleration. When a supernova explodes, it creates a blast wave that races through space. Charged particles can bounce back and forth across this shock front, gaining energy with each crossing, until they're accelerated to relativistic speeds. But the most energetic cosmic rays, the ultra-high energy ones with energies above 10 to the power of 18 electron volts, can't come from our galaxy. They're too energetic to be confined by the galactic magnetic field. They must come from extragalactic sources. Active galactic nuclei are prime candidates, but the details of how they accelerate particles to such extreme energies remain unclear. The winds from supermassive black holes, moving at relativistic speeds, might play a role, as recent research suggests. When these ultra-high-energy cosmic rays strike Earth's atmosphere, they create extensive air showers, cascades of secondary particles that spread over several square kilometers. Detector arrays like the Pierre Auger Observatory in Argentina can detect these showers and reconstruct the energy and direction of the original cosmic ray. By mapping where these cosmic rays come from, astronomers hope to identify their sources and understand the acceleration mechanisms. There's also the cosmic ray anisotropy problem. We'd expect cosmic rays to arrive uniformly from all directions if they're coming from distant sources and being scattered by magnetic fields. But observations show small but significant anisotropies, preferred directions from which more cosmic rays arrive. This could indicate nearby sources, or it could tell us about the structure of magnetic fields in our local galactic neighborhood. Now think about the Planck scale, the realm where quantum mechanics and gravity become equally important. At distances around 10 to the power of minus 35 meters and energies around 10 to the power of 19 gigaelectronvolts, space-time itself becomes quantum. Our current theories break down. We don't know how to describe what happens at the Planck scale. It might be where space-time becomes grainy or foamy, where the smooth fabric of general relativity gives way to discrete quantum structures. Some theories of quantum gravity predict that space-time at the Planck scale is a network or foam of quantum fluctuations, constantly bubbling with virtual black holes and wormholes appearing and disappearing. Other theories suggest space-time emerges from more fundamental quantum information, with space and time being illusions that arise at larger scales. These ideas are mathematically sophisticated but experimentally out of reach, at least for now. The Planck scale is also connected to the black hole information paradox. When you calculate the entropy of a black hole, you find that it's proportional to the area of the event horizon divided by the Planck area. This suggests a deep connection between black holes, thermodynamics, and quantum mechanics. The holographic principle, which states that the information content of a region of space can be encoded on its boundary, arose from studying black hole thermodynamics. If the holographic principle is true, then our three-dimensional universe is in some sense a projection of information encoded on a distant two-dimensional surface. This sounds bizarre, but it's been rigorously proven in certain toy models of quantum gravity, like the AD-SCFT correspondence discovered by Juan Meldacena. While these models don't directly describe our universe, they provide valuable insights into how quantum gravity might work. Let's not forget about the vacuum catastrophe, arguably the worst prediction in the history of physics. When you use quantum field theory to calculate the energy density of empty space, you get an answer that's about 120 orders of magnitude larger than what we observe. If the vacuum energy were really that large, the universe would have either recollapsed immediately after the Big Bang or expanded so fast that galaxies could never form. The fact that we're here at all means something is wrong with the calculation or with our understanding of the vacuum. This is intimately related to the cosmological constant problem and dark energy. The cosmological constant in Einstein's equations is mathematically equivalent to vacuum energy. But why is it so small? Various solutions have been proposed. Maybe there's a symmetry we haven't discovered that forces the vacuum energy to zero or near zero. Maybe the multiverse explains it through selection effects, with only universes having small vacuum energy being capable of forming observers. Maybe we're misunderstanding how gravity works on cosmological scales. Some physicists have suggested that the cosmological constant changes over time, transitioning from one value to another as the universe evolves. This is called quintessence, and it invokes a new field with specific properties to drive the accelerated expansion. The difference between the cosmological constant and quintessence is that the cosmological constant is truly constant, while quintessence can vary. Observations of distant supernovae and the cosmic microwave background are trying to distinguish between these possibilities, but so far, the data is consistent with a constant cosmological constant. The mystery of gamma-ray sources extends beyond gamma-ray bursts. The Fermi Gamma Ray Space Telescope has detected thousands of sources of high-energy gamma rays, and many of them remain unidentified. We can see the gamma rays, but we don't know what's producing them. Some of these sources might be previously unknown types of astrophysical objects. Others might be pulsars, rapidly rotating neutron stars whose beams of radiation sweep across Earth like cosmic lighthouses. There's also the galactic center GEVXS, a mysterious source of gamma rays coming from the region around the supermassive black hole at the Milky Way center. The emission has the wrong spectrum to be explained by known astrophysical sources. One exciting possibility is that it's the signal of dark matter particles annihilating each other. When dark matter particles meet, they could annihilate and produce gamma rays. The energy spectrum and spatial distribution of the galactic center XS match some dark matter models. But it could also be explained by a previously unknown population of millisecond pulsars in the galactic bulge. Astronomers are still trying to determine which explanation is correct. What about the mystery of time crystals? A phase of matter that was only theorized in 2012 and first created in laboratories in 2017. Normal crystals have a structure that repeats in space. A time crystal has a structure that repeats in time, with its quantum state oscillating periodically even in its lowest energy state. This seems to violate the laws of thermodynamics, but it doesn't because time crystals are driven systems, not in equilibrium. Time crystals might have applications in quantum computing, providing a way to store quantum information that's more resistant to errors. They also challenge our understanding of time symmetry and equilibrium in quantum systems. The discovery of time crystals shows that there are still new phases of matter to discover, new states that don't fit into our existing classifications. Consider also the mystery of ball lightning, rare and poorly understood electrical phenomena reported for centuries. Witnesses describe glowing spheres of light that float through the air, sometimes lasting for several seconds before disappearing. Ball lightning has been seen during thunderstorms, sometimes entering buildings through open windows or even passing through walls. For a long time, scientists were skeptical that ball lightning was real, dismissing reports as optical illusions or misidentified conventional lightning. But there have been too many consistent reports from credible witnesses to ignore. In 2012, researchers in China accidentally captured ball lightning on video and with spectrographic equipment during a thunderstorm. The data showed that the ball lightning contained silicon, iron, and calcium, suggesting it might be created when ordinary lightning strikes soil, vaporizing minerals that then form a luminous plasma ball held together by electromagnetic forces. Yet ball lightning remains mysterious. How does it stay together for so long? What prevents the plasma from dispersing immediately? Some theories invoke quantum effects or exotic electromagnetic configurations called monopoles or knots in the magnetic field. Others suggest chemical reactions involving silicon nanoparticles. We still don't have a complete explanation that accounts for all the observed properties. The mystery of the universe's missing antimatter connects to an even deeper question. Why do the laws of physics seem to have a slight asymmetry favoring matter over antimatter? The C, P, and T symmetries in physics state that the laws should be the same if you flip charge, C, flip space, P, for parity, or reverse time, T. But experiments have shown violations of these symmetries in specific processes involving the weak nuclear force. The discovery of CP violation won the Nobel Prize in Physics in 1980 and again in 2008. These violations are necessary for explaining the matter-antimatter asymmetry. But as mentioned earlier, the amount of CP violation in the Standard Model is too small. There must be additional sources, possibly involving neutrinos, possibly involving new physics beyond the Standard Model. Some grand unified theories, which attempt to unify the electromagnetic, weak, and strong nuclear forces, predict new particles called leptoquarks that can violate baryon number and lepton number conservation. These violations could have led to the matter-antimatter asymmetry in the early universe through a process called leptogenesis or baryogenesis. But we haven't detected leptoquarks or other exotic particles that would confirm these theories. The mystery of quantum tunneling is another phenomenon that defies classical intuition. In quantum mechanics, particles have a probability of passing through barriers even when they don't have enough energy to overcome them classically. This is how radioactive decay works. Alpha particles quantum tunnel through the nuclear potential barrier. It's also essential for nuclear fusion in stars. Protons can tunnel through the electromagnetic repulsion barrier and fuse together at lower temperatures than would otherwise be possible. Quantum tunneling has been verified in countless experiments, but it still feels deeply strange. How does a particle get from one side of a barrier to the other without passing through the space in between? The mathematics of quantum mechanics gives us probabilities and wave functions, but it doesn't provide a satisfying picture of what's actually happening. This is part of the larger measurement problem and the question of what quantum mechanics really means. The role of decoherence in quantum mechanics is another important piece of the puzzle. Decoherence is the process by which quantum superpositions interact with their environment and become classical. When a quantum system becomes entangled with many environmental degrees of freedom, the quantum coherence is lost, and the system behaves classically. This explains why we don't see macroscopic objects in superposition, why cats are either alive or dead and not in a quantum mixture of both states. But decoherence doesn't solve the measurement problem completely. It explains how superpositions appear to collapse from a practical standpoint, but it doesn't tell us whether there's an actual collapse or whether all the possibilities continue to exist in different branches of the wave function. Different interpretations of quantum mechanics give different answers to these questions. The mystery of the quantum Zeno effect is particularly strange. If you continuously measure a quantum system to see if it has decayed or changed state, the act of measurement prevents the decay from happening. It's as if watching a pot really does prevent it from boiling. This effect has been demonstrated experimentally and has potential applications in quantum computing for protecting quantum information from errors. What about the information processing that happens in biological systems? DNA stores genetic information with incredible density and reliability, using just 4 nucleotide bases to encode all the information needed to build and maintain a living organism. The human genome contains about 3 billion base pairs, which if printed in normal-sized text would fill about 1,000 books. Yet it's all packed into the nucleus of every cell in your body, a space only a few microns across. The machinery that reads and copies DNA is astonishingly complex and precise. Enzymes called polymerases copy DNA with an error rate of only about 1 mistake per billion nucleotides, thanks to proofreading mechanisms that detect and correct errors. This level of accuracy is essential for the faithful transmission of genetic information across generations. How did such complex molecular machines evolve? The origin of DNA replication is one aspect of the broader origin of life mystery. And what about the origin of homochirality, the fact that biological molecules have a preferred handedness? Amino acids and sugars can exist in 2 mirror image forms, called left-handed and right-handed. In living organisms, amino acids are almost exclusively left-handed, while sugars are right-handed. Why did life choose one-handedness over the other? And how did this selection occur? Some researchers think the choice was random, determined by chance fluctuations in the prebiotic soup where life originated. Others think it was influenced by external factors, like circularly polarized light from the sun or neutron stars, which could have selectively destroyed one-handedness of molecules. Still others suggest that the laws of physics themselves have a slight preference for one-handedness over the other, though this would be an incredibly subtle effect. The mystery of sleep is closer to home, but no less profound. Why do we sleep? Every animal that's been studied sleeps or exhibits sleep-like states. Sleep must be crucial for survival, or evolution would have eliminated it. When you're asleep, you're vulnerable to predators, unable to find food, unable to reproduce. The fact that sleep is universal despite these costs suggests it serves vital functions. We know that sleep is important for memory consolidation, for clearing metabolic waste from the brain, for maintaining immune function, and for numerous other physiological processes. But we still don't fully understand the mechanisms. What happens in the brain during sleep that can't happen while awake? Why do we dream? And what purpose do dreams serve? Recent research has shown that during deep sleep, cerebrospinal fluid flows through the brain more rapidly, washing away accumulated proteins and metabolites. This might be part of the reason sleep is so restorative. The phenomenon of dreams themselves is mysterious. During REM sleep, the brain is highly active, showing patterns similar to waking states, yet we're disconnected from sensory input and motor control. We experience vivid narratives, often bizarre and surreal, that feel real at the time. Some researchers think dreams are the brain's way of processing memories and emotions, replaying experiences and integrating them into long-term memory. Others think dreams are essentially random, byproducts of the brain's activity during sleep without any particular function. Lucid dreaming adds another layer. Some people can become aware that they're dreaming while the dream is happening and can even control aspects of the dream. Studies have shown that lucid dreamers can signal from inside the dream using predetermined eye movements, which are detected by equipment monitoring their sleep. This proves that lucid dreamers are genuinely conscious during sleep, aware of both the dream world and the fact that they're dreaming. What does this tell us about consciousness? If you can be conscious while asleep and dreaming, then consciousness doesn't require waking sensory input. It's generated internally by the brain, creating a model of reality that can run independently of external stimuli. This supports theories that view consciousness as a controlled hallucination, a model the brain constructs to make sense of sensory data and internal states. The placebo effect is another mysterious phenomenon involving consciousness and physiology. When people believe they're receiving treatment, they often experience real improvements in symptoms, even if the treatment is inert. The placebo effect can reduce pain, alleviate depression, lower blood pressure, and affect numerous other conditions. It's not just psychological. Brain imaging studies show that placebos activate the same neural pathways as real drugs. Even more bizarrely, there's a nocebo effect, where negative expectations cause actual harm. If people believe a harmless substance will make them sick, they often develop real symptoms. This demonstrates the profound influence of mind over body, but we don't understand the mechanisms. How do beliefs and expectations translate into physiological changes? What's the pathway from thought to biochemistry? Recent research has found that the placebo effect involves the release of endorphins and other neurotransmitters, changes in brain activity, and modulation of the immune system. The expectations and beliefs activate these systems, producing measurable biological effects. This has important implications for medicine. Maybe the ritual of treatment, the doctor-patient interaction, and the patient's expectations are all contributing to healing in ways we're just beginning to understand. Now, consider the mystery of mathematical truth. Mathematics seems to exist independently of the physical world. The Pythagorean theorem was true before humans discovered it, and it would remain true even if humans went extinct. Pi has the same value everywhere in the universe. The Mandelbrot set, with its infinitely complex patterns, exists in the realm of mathematical abstraction regardless of whether anyone ever computes it. This leads to deep questions about the nature of mathematical reality. Is mathematics discovered or invented? Do mathematical objects like numbers and sets really exist in some Platonic realm? Or are they just useful fictions created by human minds? The physicist Eugene Wigner wrote about the unreasonable effectiveness of mathematics in describing the physical world. Why should abstract mathematical structures that mathematicians develop for their own sake turn out to be exactly what's needed to describe nature? Some physicists take this so seriously that they propose the mathematical universe hypothesis, the idea that reality itself is mathematical, that the universe is literally a mathematical structure. In this view, different mathematical structures correspond to different possible universes, and we inhabit just one of them. This is Max Tegmark's Level 4 multiverse, the most radical version of the multiverse idea. Critics argue that this confuses the map with the territory, that mathematics is just a language we use to describe reality, not reality itself. But the deep connection between mathematics and physics is undeniable. Equations discovered for purely abstract reasons have turned out to describe real physical phenomena. The Dirac equation, derived from theoretical considerations about quantum mechanics and relativity, predicted the existence of antimatter before it was discovered. The question of why mathematics works so well in physics remains one of the deepest mysteries in the foundations of science. It suggests a profound connection between the human mind, mathematical structures, and the physical universe, a connection we don't yet understand. As we approach the limits of what we know, we must confront the possibility that some of these mysteries might never be solved. There could be fundamental limits to what we can discover, boundaries beyond which human knowledge cannot go. Maybe some questions are intrinsically unanswerable, not because we lack the intelligence or technology, but because the nature of reality itself prevents us from knowing the answers. The observable universe has a finite size, limited by the distance light has traveled since the Big Bang. Beyond that horizon, there could be infinite expanses of space we'll never observe because light from those regions hasn't had time to reach us and never will due to the acceleration of cosmic expansion. If the multiverse exists, other universes are by definition beyond our ability to detect directly. We can only infer their existence through indirect reasoning and mathematical consistency. Quantum mechanics might place fundamental limits on what we can know. The uncertainty principle tells us that we can't simultaneously know a particle's position and momentum with perfect precision. Maybe there are similar limits on other combinations of properties, limits that prevent us from having complete knowledge of reality. Some physicists have suggested that information itself is bounded, that there's a maximum amount of information that can be stored in a given region of space, related to the holographic principle and black hole entropy. But throughout history, people have declared certain questions unanswerable, only to be proven wrong by future discoveries. The nature of matter was once thought to be beyond human ken, yet we've discovered atoms, protons, electrons, quarks. The age and size of the universe were unknown mysteries a century ago, yet now we can measure them with precision. The structure of DNA, the existence of gravitational waves, the accelerating expansion of the universe, all these were unknown and perhaps seemed unknowable until the right observations and theories came along. So perhaps we should be optimistic. Perhaps the mysteries we face today will yield to future insights, new technologies, and deeper understanding. The next breakthrough in physics might come from an unexpected direction, solving multiple puzzles at once. Or it might come from painstaking experimental work, slowly accumulating data until patterns emerge. What's certain is that the quest to understand these mysteries is one of the most noble and important endeavors humans can undertake. It's an attempt to comprehend our place in the cosmos, to understand the rules by which reality operates, to see beyond the surface appearance of things to the underlying truth. And even if we never solve all these mysteries, the attempt itself is worthwhile. It teaches us humility in the face of cosmic vastness, wonder at the intricacy and strangeness of nature, and appreciation for the magnificent universe we're privileged to inhabit. Every mystery we've explored represents a frontier of human knowledge, a place where our understanding gives way to questions. But these are not barriers, they're invitations. They invite us to think more deeply, to observe more carefully, to imagine more boldly. They remind us that for all our technological advancement and scientific achievement, we're still children in the cosmic scheme of things, just beginning to understand the world around us. And perhaps that's exactly as it should be. Perhaps the universe is meant to be mysterious, meant to challenge us, meant to inspire generations of scientists and thinkers to push forward into the unknown. Perhaps these mysteries are gifts, keeping us curious, keeping us humble, keeping us reaching for understanding. As you continue your journey through life, carrying these mysteries with you, remember that you're part of something extraordinary. You're a pattern of atoms that became conscious, a piece of the universe that woke up and started asking questions about itself. You're living in a time when we can peer back to the first moments after the Big Bang, detect gravitational waves from colliding black holes, and contemplate the possibility of other universes beyond our own. The 30 deepest mysteries of the universe aren't just abstract problems for physicists and cosmologists. They're part of your story too, because you're made of stardust. Your existence depends on the same dark matter and dark energy that shaped the cosmos, and your consciousness might be connected to quantum processes that link you to the fundamental fabric of reality. So when you look up at the night sky, when you contemplate the vastness of space and time, when you wonder about your place in it all, know that you're participating in the universe's greatest adventure, the quest to understand itself. But our journey through the cosmos's deepest mysteries isn't complete. There are still more enigmas to explore, more questions that pierce through the veil of what we think we know. Let's delve into the remaining mysteries that continue to baffle and inspire us. Consider the nature of information itself. In the digital age, we're surrounded by information encoded in bits, zeros, and ones. But what is information at the most fundamental level? Physicist John Archibald Wheeler proposed it from bit, the idea that information is more fundamental than matter and energy, that the physical universe emerges from information. In quantum mechanics, information plays a crucial role. The quantum state of a system contains all the information about that system, and quantum operations manipulate this information in ways that have no classical analog. The limits of information processing are themselves mysterious. In 2013, Seth Lloyd calculated the maximum amount of computation the universe could have performed since the Big Bang, based on its mass-energy content and age. The number is mind-boggling but finite. About 10 to the power of 120 operations on about 10 to the power of 90 bits. If the universe is a computer, this is its computational capacity. But what is it computing? Is the universe literally performing a calculation, or is this just a metaphor? The black hole information paradox ties directly into questions about information. If information cannot be destroyed, as quantum mechanics insists, then what happens when it falls into a black hole? Some physicists think the information is somehow encoded on the event horizon, stored in subtle correlations in the Hawking radiation that the black hole emits over its lifetime. Others think information is preserved inside the black hole and gets released if the black hole eventually transitions into a white hole. Still others propose more radical solutions involving modifications to quantum mechanics or general relativity. Recent work on the firewall paradox has made this even more puzzling. If you try to trace what happens to information falling into an old, evaporating black hole, you reach a contradiction. Either there's a violent firewall of high-energy particles at the event horizon that incinerates anything crossing it, violating the equivalence principle of general relativity, or information is duplicated, violating the no-cloning theorem of quantum mechanics, or the interior of the black hole doesn't exist in the way we think it does. All three options seem impossible, yet one of them must be true. What about the mystery of fine structure constant, one of the fundamental constants of nature? This dimensionless number, approximately 1 divided by 137, determines the strength of the electromagnetic interaction. It appears in equations throughout physics, from the energy levels of hydrogen atoms to the behavior of light. But we have no idea why it has this particular value. Richard Feynman called it one of the greatest damn mysteries of physics, a magic number that comes to us with no understanding. If the fine structure constant were slightly different, the universe would be dramatically altered. If it were larger, stars would burn out faster and might not produce the heavy elements necessary for life. If it were smaller, stars might not ignite at all. The precise value seems finely tuned, which brings us back to questions about anthropic reasoning and the multiverse. Is there a deeper theory that predicts the fine structure constant's value? Or is it just an environmental accident in our particular bubble universe? Some physicists have speculated that the fundamental constants might not be constant after all. They could vary over cosmic time or from place to place in the universe. Several experiments have searched for time variation in the fine structure constant by analyzing light from distant quasars, looking for subtle shifts in the spectral lines. Some studies have claimed to detect tiny variations, but these results remain controversial and haven't been independently confirmed. The mystery of cosmic voids deserves deeper exploration. When you map the distribution of galaxies on the largest scales, you find enormous regions of space with very few galaxies. The largest known void, the VOID void discovered in 1981, is about 330 million light-years in diameter and contains only about 60 galaxies, far fewer than expected for a region that size. These voids aren't completely empty, but they're remarkably underdense compared to the cosmic average. How did these voids form? In the standard picture, they're regions where the initial density was slightly lower than average. Over billions of years, matter flowed out of these regions toward the denser areas, creating the filamentary structure of the cosmic web. But the detailed physics of void formation is still being investigated. Voids provide a unique laboratory for studying dark energy and modified gravity theories, because in these low-density regions, the effects of dark energy might be more pronounced. The Eridanus supervoid is particularly interesting. This is an enormous underdense region that might explain the CMB cold spot mentioned earlier. If photons from the cosmic microwave background pass through such a large void, they lose energy through a process called the integrated Sachs-Wolf effect, creating a colder spot in the CMB. But calculations suggest that even the Eridanus supervoid isn't quite large or underdense enough to fully explain the cold spot, leaving some mystery remaining. Let's talk about the mystery of stellar metallicity, the abundance of elements heavier than hydrogen and helium in stars. The first stars, called population 3 stars, formed from pristine hydrogen and helium left over from the Big Bang. They would have been massive, luminous, and short-lived, exploding as supernovae and enriching the surrounding gas with heavier elements. Subsequent generations of stars formed from this enriched gas, so later stars have higher metallicity. But we've never observed a population 3 star directly. They're all dead, having lived and died billions of years ago when the universe was young. Astronomers have searched for them in the most distant galaxies, where we're looking back in time to the early universe. But even there, the stars show some level of metal enrichment. The James Webb Space Telescope might finally detect population 3 stars, or at least their characteristic signatures in the spectra of early galaxies. The distribution of stellar metallicity also tells us about the history of star formation and element production in galaxies. By measuring the metallicity of stars at different distances from the galactic center and at different ages, astronomers can reconstruct how galaxies built up their complement of heavy elements over time. This forensic approach, called galactic archaeology, is revealing the complex history of how galaxies grew and evolved. The mystery of planet formation is closer to home but still not fully solved. We understand the basic picture. Planets form in disks of gas and dust around young stars, with dust grains sticking together to form larger and larger objects, eventually growing into planets. But the details are tricky. How do dust grains overcome electrostatic barriers to stick together? How do planetesimals grow from meter-sized objects, which should rapidly spiral into the star due to drag from the gas disk, to kilometer-sized objects where gravity takes over? Recent observations of protoplanetary disks with ALMA and other telescopes are revealing intricate structures, gaps, rings, and spirals in the dust distribution. These features might be carved out by forming planets, or they might be due to instabilities in the disk itself. We're also finding that planet formation seems to be efficient and common, with most stars hosting at least one planet. This increases the likelihood that Earth-like planets exist elsewhere, raising the stakes in the search for life beyond our solar system. The diversity of planetary systems is astounding. We found hot Jupiters, gas giants orbiting closer to their stars than Mercury orbits the Sun. We found super-Earths, planets more massive than Earth but lighter than Neptune, a class that doesn't exist in our solar system. We found rogue planets drifting through interstellar space, unbound to any star. Each discovery expands our understanding of what's possible in planet formation and challenges our theories. The habitable zone, the range of distances from a star where liquid water could exist on a planet's surface, is itself more complex than originally thought. It depends not just on distance but on the planet's atmosphere, its geological activity, its magnetic field, and many other factors. Europa and Enceladus have subsurface oceans despite being far outside the traditional habitable zone, kept liquid by tidal heating. Maybe habitable zones should include moons of gas giants or rogue planets with thick hydrogen atmospheres that insulate their surfaces. The mystery of quasar absorption lines has taught us much about the universe between us and distant quasars. When light from a quasar travels toward Earth, it passes through clouds of gas in the intergalactic medium. These gas clouds absorb light at specific wavelengths, creating dark absorption lines in the quasar's spectrum. By analyzing these lines, astronomers can study the distribution, temperature, and composition of gas across billions of years of cosmic history. One particularly important set of absorption lines is the Lyman alpha forest, numerous narrow lines caused by neutral hydrogen absorbing ultraviolet light. The Lyman alpha forest provides a detailed map of the cosmic web, showing where gas is concentrated in filaments and where it's evacuated from voids. It also constrains models of reionization and the thermal history of the intergalactic medium. Occasionally, astronomers detect strong absorption systems called damped Lyman alpha absorbers, which have high column densities of neutral hydrogen. These are thought to be proto-galaxies or the disks of forming galaxies, regions where hydrogen is dense enough to shield itself from ionizing radiation. Studying damped Lyman alpha absorbers gives us a unique window into galaxy formation and evolution. The cosmic neutrino background is another prediction of the Big Bang model that we haven't yet detected directly. About 1 second after the Big Bang, when the universe cooled below 10 billion Kelvin, neutrinos decoupled from other matter and radiation. Since then, they've been streaming freely through space, cooled by cosmic expansion to a temperature of about 2 Kelvin today. These relic neutrinos should fill the universe with a density of about 300 per cubic centimeter. But detecting them is incredibly difficult. At such low energies, neutrinos interact even more weakly than usual with ordinary matter. No current or planned experiment can detect the cosmic neutrino background directly. However, its existence has indirect effects on the large-scale structure of the universe and on the cosmic microwave background. The neutrinos contribute to the radiation density in the early universe, affecting the expansion rate and the growth of density fluctuations. If we could somehow detect the cosmic neutrino background, it would provide a snapshot of the universe at 1 second old, much earlier than the CMB snapshot at 380,000 years. This would test our models of the very early universe and might reveal new physics. It's a holy grail of cosmology, but it may remain forever out of reach. The mystery of the WOW signal continues to intrigue those interested in the search for extraterrestrial intelligence. In August 1977, astronomer Jerry Emmon was analyzing radio telescope data from the Big Ear Observatory when he noticed an incredibly strong, narrowband signal that lasted 72 seconds. The signal was so striking that Emmon circled it on the printout and wrote "Wow" in the margin, giving the signal its name. The WOW signal had many characteristics we'd expect from an artificial transmission. It was at 1,420 MHz, close to the natural emission line of hydrogen and a frequency protected from terrestrial transmission. It was narrowband, much narrower than any known natural astrophysical source. And it appeared to come from a specific direction in the constellation Sagittarius. But despite numerous follow-up observations, the signal has never been detected again. What was the WOW signal? Was it an alien transmission? A natural but rare astrophysical phenomenon? A glitch in the equipment? A terrestrial signal that somehow leaked through the filters? We may never know. Some researchers think it could have been a signal from a passing comet, with a hydrogen-rich coma producing maser emission. Others maintain it had all the hallmarks of an artificial signal. The mystery persists, a tantalizing hint that we might not be alone. The broader search for extraterrestrial intelligence continues through projects like SETI, which use radio telescopes to scan the sky for artificial signals. The Breakthrough Listen initiative, funded by philanthropist Yuri Milner, is conducting the most comprehensive search yet, monitoring millions of stars and nearby galaxies. So far, no confirmed alien signals have been found, but the search continues. Should we be transmitting messages ourselves, or should we stay quiet? This question has sparked debate among scientists. Some argue that actively broadcasting our presence is reckless, potentially inviting hostile aliens to find us. Others counter that any civilization capable of reaching us would already know we're here from our inadvertent radio and television broadcasts leaking into space, so deliberate messages make little difference. The debate touches on deep questions about risk, ethics, and humanity's place in the cosmos. The mystery of time perception in living organisms is another frontier. How do animals and humans perceive the passage of time? We can estimate durations, remember sequences of events, and anticipate the future, but the neural mechanisms underlying these abilities are still being investigated. There's no single clock in the brain. Instead, time perception emerges from distributed neural networks that integrate information about rhythms, changes, and sequences. Interestingly, time perception is highly subjective and can be distorted. During moments of high stress or fear, time seems to slow down, events unfolding in slow motion. This is thought to be due to enhanced memory encoding during stressful situations. We remember more details, and when we recall the memory, it seems to have lasted longer. Drugs, meditation, and certain mental states can also alter time perception, suggesting that our experience of time is constructed by the brain rather than being a direct reading of objective time. Some animals perceive time differently than humans. Small animals with fast metabolisms often experience the world in slow motion, their neural processing running at higher speeds. This is why a fly can dodge your hand so easily. From the fly's perspective, your hand is moving in slow motion, giving it plenty of time to react. The critical flicker fusion frequency, the rate at which a flickering light appears continuous, varies across species and correlates with their perception of time. The arrow of time in biology is intimately connected to the arrow of time in thermodynamics. Living organisms maintain their complex, ordered structures by consuming energy and increasing the entropy of their surroundings. You eat food, a highly ordered form of energy, and excrete waste, a less ordered form. Your body stays organized at the expense of increasing disorder in the environment. This is how life evades the second law of thermodynamics locally while obeying it globally. But the origin of this biological arrow of time goes back to the origin of life itself. How did the first self-replicating molecules harness energy flows to maintain their organization? How did metabolisms evolve to extract energy from chemical gradients? These questions connect the mystery of life's origin to the fundamental thermodynamics of the universe. The phenomenon of synchronization in nature is a mystery that spans scales from subatomic particles to living organisms to astronomical objects. Synchronization occurs when coupled oscillators lock their phases, oscillating in step with each other. Fireflies flash in unison. Pendulum clocks hanging on the same walls sync up. Neurons in the brain fire synchronously during certain cognitive tasks. Even the orbits of planets can become synchronized through gravitational interactions. The mathematics of synchronization, pioneered by physicists like Art Winfrey and Stephen Strogatz, reveals universal principles that apply across vastly different systems. The transition from incoherent oscillation to synchronized behavior often happens abruptly at a critical coupling strength, similar to a phase transition in physics. Understanding synchronization helps us comprehend how order emerges from chaos, how billions of independent components can act as a unified whole. In the brain, synchronization of neural oscillations is thought to be crucial for binding together different aspects of perception into a unified conscious experience. When you see a red apple, neurons encoding color, shape, location, and meaning synchronize their firing, creating a coherent representation. Disruptions in neural synchronization are associated with conditions like epilepsy, schizophrenia, and Parkinson's disease, highlighting its importance for normal brain function. The mystery of animal navigation is truly remarkable. Sea turtles return to the exact beach where they hatched to lay their own eggs, having traveled thousands of kilometers across featureless ocean. Salmon navigate back to the specific stream where they were born. Monarch butterflies migrate thousands of miles to specific forests in Mexico, following routes they've never traveled before. How do these animals navigate with such precision? Different species use different navigation mechanisms. Some use the sun or stars as compasses, compensating for their movement across the sky. Others use Earth's magnetic field, detecting subtle variations in field strength and direction using magnetite crystals in their bodies or quantum effects in certain proteins. Still others use olfactory cues, following chemical trails in the water or air. Many species probably use a combination of these mechanisms, integrating multiple sources of information. The discovery of quantum effects in bird navigation was particularly surprising. European robins, and probably other migratory birds, can detect magnetic fields using a protein called cryptochrome in their eyes. When blue light strikes cryptochrome, it creates a pair of entangled electrons whose quantum states are sensitive to magnetic fields. This quantum compass allows birds to literally see magnetic fields as patterns of light and dark overlaid on their visual field. It's one of the few confirmed examples of quantum biology where quantum mechanics plays a functional role in a living organism. Think about the implications. Evolution has discovered how to harness quantum entanglement for a practical purpose. If birds can do it, what other quantum phenomena might be exploited by biological systems? We're only beginning to understand how quantum mechanics operates in the warm, wet, noisy environment of living cells, traditionally thought to destroy quantum coherence too quickly for it to be useful. The mystery of the Cambrian explosion is one of the most dramatic events in the history of life on Earth. For billions of years, life was exclusively microscopic, simple single-celled organisms that left little fossil evidence. Then, about 540 million years ago, in a geological instant, complex multicellular life exploded in diversity. Most of the major groups of animals we see today appeared during a period of about 20 million years. What caused this sudden burst of innovation? Several factors probably contributed. The evolution of hard body parts like shells and skeletons made animals more likely to fossilize and may have triggered an evolutionary arms race between predators and prey. Rising oxygen levels in the ocean and atmosphere would have enabled larger, more active animals. Genetic innovations like the Hox genes, which control body plan development, allowed for more complex and diverse body forms. But there's still debate about whether the Cambrian explosion was really as sudden as it appears. Maybe complex animals existed earlier but didn't fossilize well, or we haven't found their fossils yet. Recent discoveries of soft-bodied fossils from the Ediacaran period, just before the Cambrian, show that complex multicellular life was already emerging. The Cambrian explosion might have been less of a sudden explosion and more of a gradual radiation that accelerated at some point. Regardless of its exact pace, the Cambrian explosion fundamentally changed the biosphere. It established the basic body plans and ecological relationships that persist to this day. It was a crucial step in the evolution of complexity, showing that life can undergo rapid transformative changes when conditions are right. The Great Oxygenation Event, about 2.4 billion years ago, was another transformative moment. Before then, Earth's atmosphere contained little free oxygen. Most organisms were anaerobic, living without oxygen or even poisoned by it. Then cyanobacteria evolved photosynthesis, splitting water molecules and releasing oxygen as a waste product. Over hundreds of millions of years, oxygen accumulated in the atmosphere, fundamentally changing the planet. The rise of oxygen enabled aerobic respiration, a much more efficient way of extracting energy from food than anaerobic metabolism. This made possible larger, more complex organisms with higher energy demands. But the initial rise of oxygen was probably catastrophic for most existing life, used to an oxygen-free world. It's been called the oxygen catastrophe or the Great Oxidation Event, and it may have caused the first major mass extinction. The oxygenation of the atmosphere also changed the chemistry of rocks and minerals on Earth's surface. Rusted iron formations, distinctive red bands of oxidized iron, appeared in the geological record, marking the transition. These formations are some of the clearest evidence we have of ancient environmental changes preserved in rock. What would have happened if photosynthesis had never evolved? Would life have remained simple and microscopic, eking out an existence using chemical energy from geothermal sources? Or would some other metabolic innovation have eventually allowed complex life to emerge? We can't know for sure, but it's a reminder of how contingent the history of life is, how much depends on specific evolutionary innovations at crucial moments. The mystery of convergent evolution shows that evolution is not entirely random. Given similar environmental pressures, completely unrelated organisms often evolve similar solutions. Eyes have evolved independently dozens of times. Wings evolved separately in insects, birds, bats, and pterosaurs. The streamlined body shape of sharks, dolphins, and ichthyosaurs arose independently in fish, mammals, and reptiles. These convergences suggest that there are optimal solutions to certain problems, that the space of possible designs is constrained by physics and functionality. But convergent evolution also has limits. Certain body plans and capabilities have evolved only once or a few times. Powered flight evolved in insects, pterosaurs, birds, and bats, but not in other major animal groups. Intelligence at human levels evolved only once, in our lineage. These rare innovations might require very specific circumstances, or they might be intrinsically difficult to evolve. Understanding convergent evolution helps us predict what alien life might be like. If life exists on other planets, it will face similar physical constraints and challenges. Gravity, thermodynamics, and chemistry work the same everywhere. So maybe alien life will converge on some of the same solutions Earth life has found. Sensors for detecting light and chemicals, mobility for navigating the environment, information storage systems like DNA. But alien life will also be shaped by its specific environment and evolutionary history, leading to features we can't anticipate. The mystery of extinction is the flip side of the mystery of evolution. Throughout Earth's history, species have gone extinct at a background rate as environments change and new species outcompete old ones. But periodically, something catastrophic happens, and extinction rates spike. These mass extinctions have eliminated most species on Earth, resetting the evolutionary clock and allowing survivors to diversify and fill empty niches. The most famous mass extinction ended the age of dinosaurs 66 million years ago. We now know it was caused by an asteroid impact in what is now the Yucatan Peninsula. The impact threw massive amounts of dust and debris into the atmosphere, blocking sunlight and causing a global winter. Plants died, herbivores starved, and the whole food chain collapsed. But some species survived: small mammals, birds, crocodilians, and others. The survivors diversified in the aftermath, leading eventually to the world we inhabit today. Earlier mass extinctions had different causes. The Permian-Triassic extinction, the worst in Earth's history, killed over 90% of marine species and 70% of land species about 252 million years ago. The causes are still debated, but likely involved massive volcanic eruptions in Siberia, releasing enormous amounts of greenhouse gases and triggering runaway climate change, ocean acidification, and oxygen depletion. Are we currently in the midst of a sixth mass extinction caused by human activity? Many biologists think so. Species are going extinct at rates hundreds or thousands of times higher than the background rate, primarily due to habitat destruction, pollution, and climate change. We don't know how this will play out or what the long-term consequences will be, but the evidence suggests we're dramatically altering the biosphere in ways that future geologists will detect in the rock record, if intelligent observers exist to study it. The mystery of aging and death is particularly poignant for us. Why do organisms age and eventually die? From an evolutionary perspective, aging is puzzling. Natural selection favors genes that increase reproductive success. So why hasn't evolution eliminated aging? The answer is that natural selection's power declines with age. Genes that affect early life and reproduction are strongly selected, while genes that affect late life, after most reproduction has occurred, are under weak selection. Harmful mutations that only manifest late in life can accumulate, because selection doesn't effectively remove them. Beneficial mutations that extend lifespan beyond the reproductive years provide little evolutionary advantage in wild populations, where most individuals die young from predation, disease, or accidents. But aging is also genetically controlled and can be modified. Mutations in specific genes can double the lifespan of worms, flies, and mice. Caloric restriction extends lifespan in many organisms, possibly by activating cellular stress response pathways that increase maintenance and repair. Understanding the mechanisms of aging might allow us to intervene, slowing or reversing age-related decline. Some organisms don't seem to age at all. Certain jellyfish can revert to earlier developmental stages, effectively resetting their biological clock. Hydras, simple freshwater animals, show no signs of senescence and might be biologically immortal. Lobsters continue growing throughout their lives and don't show typical signs of aging, though they do eventually die from other causes. These exceptions prove that aging is not inevitable, that it's a biological process that can potentially be manipulated. The ultimate question remains: what is the universe, and why does it exist? This brings us full circle to where we began, contemplating mysteries so vast that they strain the limits of human comprehension. We've invented mathematics, built particle accelerators and telescopes, developed theories of astonishing sophistication and predictive power. And yet the deepest questions remain tantalizingly out of reach. Is the universe finite or infinite? Does it have a boundary or edge? What lies beyond the observable horizon? These questions might be unanswerable in principle, not just in practice. If other regions of space are forever beyond our light cone, we can never observe them directly. We can only speculate based on extrapolation from what we can see. Does the universe have a purpose, or is it just a brute fact, existing without reason or meaning? Science can describe how the universe works, can trace its history back to the first moments after the Big Bang, but it cannot tell us why there is something rather than nothing, or whether the universe has any ultimate significance. These are questions that venture into philosophy and even theology, beyond the realm of empirical science. Different people find different answers based on their worldviews, values, and personal experiences. But the questions themselves are universal, arising from our deep need to understand our place in the cosmos. As we conclude this exploration of the 30 deepest mysteries of the universe, remember that these are not isolated puzzles. They're interconnected, each one touching on others, hinting at a deeper unity we haven't yet grasped. Dark matter and dark energy shaped the large-scale structure that gave rise to galaxies where stars formed and created heavy elements. Those elements made possible planets and life. Life evolved consciousness, which asks questions about dark matter and dark energy, bringing the circle closed. You are a participant in this grand cosmic story, not just an observer but an active agent. Your existence required 13.8 billion years of cosmic evolution, the births and deaths of countless stars, the formation of the solar system, the evolution of life on Earth. You are made of atoms forged in stellar furnaces, animated by energy from the sun, aware of your place in space and time. The mysteries we've explored will occupy scientists for generations to come. Some may be solved in your lifetime. The next great discovery could come tomorrow. A breakthrough that revolutionizes our understanding just as quantum mechanics and relativity did a century ago. Or these mysteries might persist for centuries, waiting for insights and technologies we can't yet imagine. But whether or not these mysteries are solved, the quest itself matters. It defines us as a species uniquely capable of pondering our origins and fate, uniquely driven to push beyond the boundaries of the known. We are the universe waking up, looking at itself, asking why. And that question, that endless exploration of mystery upon mystery, might just be the deepest mystery of all, the strangest and most wonderful fact about this strange and wonderful universe we call home.